We are at time. Jenny, you gonna
Yeah, maybe.
give
So
another
we,
minute?
yeah, I think we can wait maybe 1 minute and then start.
Okay. You probably don't have 10 minutes of chair talking to.
Yeah, I have very brief talk actually,
Okay.
just to remind some information and that's all. Okay.
Jenny, do you want me to share the slides?
Uh, After I finish my very brief talk, will you be able to share them and continue with the moderating process of the whole session? Actually, not one but two sessions.
That's good.
Yeah. Okay. Do you have the slides?
Yeah, I have them.
Oh, great. So let's start. Today we have the second day of our workshop on measuring network quality for end users. And we have a very interesting agenda for today. We will have 4 sessions. Every session will have several presentations, and after that, rather long and interesting discussion. And just remind that, so all of you are welcome to participate in the discussion, and to be included, please write plus Q in the chat during the presentation or during the discussion. And also we have, please take into account that we ask all participants to limit the duration of the talk by 16 seconds, just to allow more people to participate in the discussion. And if you have, if you want to answer to a comment which is currently being said, so please either raise your hand or indicate somehow in the chat to ask the moderator to give you a talk. So also just a reminder, we have a text discussion in the Slack, and the link to the Slack will be copied to the chat after my very brief presentation. So I think that we have a lot to discuss today. So let's start. And I introduce you, Christoph, who will chair the first 2 sessions of today's of today. Yeah. So Christoph, I'm stopping sharing my screen, and please share.
Hello. So let's get started right away with Jonathan on metrics helpful in assessing internet quality.
Okay, hi, thanks. Chris, next slide, please. So today I'll be sharing with you some metrics that were developed over the course of multiple years of deploying a solution that promises to improve users' internet quality with a router that automatically adapts to their line. So some of these metrics were necessary for the automation functions, but many were necessary for triaging issues and to inform and alert users about anomalies with their service. First of these metrics is an accurate determination of line capacity, which actually is harder to nail down than one would think. It takes multiple samples at varying times across multiple days to really profile a line, since those are not always consistent. From our data set, we find that about 36% of lines vary by more than 10% over our measurement periods. Another critical aspect is accounting for all of the local traffic, not just that traffic from a synthetic test. So this must be performed by the bottleneck router as it sees all traffic from all devices. A end user device can't fully profile that. So during these capacity tests, the capture of latency under working loads is performed to determine buffer bloat levels with the traffic manager both disabled and later with the traffic manager enabled to confirm whether settings are appropriate. And just like capacity, latency metrics from the router truly accurately profile current internet link performance and allow for accurate reporting. Performing these latency metrics on an ongoing basis allows determining whether current QoS settings are sufficient to mitigate buffer bloat and are used to refine these settings dynamically. Our data shows that most lines have some dynamic change required over its lifetime, with cable lines having about 72 dynamic changes since deployment and DSL having around 144, reflecting the fact that limited capacity lines really do have more susceptibility to capacity-induced sag. The depicted graph is a good illustration of a cable line with some significant sag in the evenings, which is usually due to backhaul or local loop congestion, requiring the traffic manager to be adjusted down until latencies are acceptable. The system will also dynamically adjust upwards when latencies seem to have recovered. This preserves a high quality of user experience, and in this case, there's still enough capacity for most online activities. This user is perfectly happy with their internet service. This reinforces points made in other papers that QoE at the end user level does not necessarily correlate with line capacity alone. A stable, low latency line wins most every time. Next slide, please. One thing rarely discussed are link stability metrics, which are vital to good QoE. Link loss is an obvious one, so logging and reporting this helps users and their ISPs have facts to inform them about when these events occur. This also helps people understand when loss of connectivity is due to local events like poor Wi-Fi connectivity. But the metric I'd like to share a bit more about is discussed further in our document, and this is the unstable line, which we define as an increase in latencies with little to no load. Often, this is a transient phenomenon, usually caused by failing modems or backhaul congestion, or as we frequently use it, to detect a cascaded router scenario where traffic is bypassing our traffic manager in the IQ router, and this is usually due to somehow the ISP's all-in-one Wi-Fi being remotely enabled. In our data set, we see that more than a quarter of deployments see this at some point, and quite a few deployments have just a tremendous amount of these. We also use this unstable metric to determine if we need to now bypass our dynamic adjustments, since reacting to phantom latencies generally does not help. So next slide, please. Finally, I'd like to mention that there are metrics we'd love to see the industry adopt around local metrics, which we see as important to help users and providers understand the contrast between local and the link level performance. We've had customers with perfect buffer bloat scores from wired connections have very poor scores when using power line or Wi-Fi links. So documenting those as a start is helpful in getting users to fix their local QoE issues. We believe that an on-router service or a locally run app on a wired PC would allow quantifying this, and that a standard API and a metric would make adoption broader. Our hope is that an outcome of this workshop is that we progress on something like a local RPM service interface definition. That way I can see what my local versus my public internet performance is like. So in summary, ongoing metrics are required to correctly profile the line capacity. Ongoing passive and active latency metrics are necessary to dynamically adapt the QoS, and that reporting link states is very helpful in enabling users and service providers to understand common line issues, and that we really hope to see a standardized means of determining local network characteristics. Thanks, and look forward to your questions.
Thank you, Jonathan. Are there any clarifying questions or comments in the audience? I saw Bob had one question, but he seems to have clarified it himself already. Okay, then we go on to the next presentation.
Okay.
This time, Vijay on measuring network experience meaningfully, accurately, and scalably.
Thank you very much. And indeed, thank you very much for the opportunity to present my position. So I'm Vijay. I'm a professor at UNSW Sydney, which is in Australia. Have been working in the area of QoS and QoE for quite a while. And in fact, a couple of years back, decided to commercialize some of my ideas into a startup called Canopus Networks, where I'm also the current CEO. So if you can move to the next slide. So there are 2 points that I would like to take the opportunity to make today. The first of which is that we take the position that experience or quality of experience should, we would very much like to see it from the user's perspective. Obviously in Australia, the regulator measures things like speed, and I've just put a sample graph of what consumers or users get to see in the latest report that came out a couple of weeks back. And frankly, as a user, I'm not getting a lot of information out of this in the sense that the speeds are all like fairly close to each other. The gap is very narrow. In fact, the top 3 are within 1% of each other. And if anything, this race for speed is causing the economics for ISPs to really race to the bottom. Of course, one could augment speed with things like latency and loss. But again, these are things the user does not really perceive or understand what it actually means, because sometimes loss and latency can be absorbed by the application. So we definitely take the view that it's quite useful to measure experience from the perspective of the consumer, exactly how they think of experience. And by that, we mean, for example, streaming video. If you're watching Netflix or Disney Plus or Prime or what have you, you're very concerned as a consumer about, well, I've just bought a 4K TV. Am I really getting the video at the best possible resolution given the investment I've made into a device such as a TV? Is my video freezing? Am I getting that buffering or that spinning wheel? So those would be the most pertinent things to from a user's perspective. And in contrast to showing the speed as in the plot above, we could show them with the different options they have for ISPs. In Australia, we call them RSPs because they're retail, because the access network is actually nationalized by the government. So how would the RSPs or ISPs compare in terms of their capability to serve video at the highest available resolution? And you can go down further and break it up by the provider of video. Obviously, YouTube is different to Netflix, is different to Disney Plus, and so on and so forth. You could do the same for gaming. Users who are gamers would very much like to know if they're playing Fortnite or Counter-Strike or Apex Legends, how consistent is the latency they get and how low is it while they're playing, because we know that any jitter can mean gunshots not taking effect or teleporting in the game. So, and being able to show that clearly, as on the right bottom plot, you can see the green means experience has been good, orange is mediocre, and red is bad. And this can be customized to the title of the game. So what's shown here is aggregated across shooting titles, but you could even break it down by individual game titles, and you could equally show this experience measure for role-playing games, or strategy games, or sports games like FIFA and so on. And you could do the same for conferencing applications by telling users exactly what is the relative performance on your ISP in terms of getting stutters and dropouts on your conference calls. And all these measurements can be done passively on real applications in the real natural operating environment, rather than via synthetic bursts of speed tests or via latency probes. So that was the first point, trying to really show these metrics that are very easy for the user to understand and appreciate and relate to. If you could move on to the second slide, that will be the second point and final point we want to make today, which is, and sorry, you can click on to show the animations as well. Yeah, thank you. So the second point we'd like to make is, it's all great to talk about trying to show all those very application-centric metrics, but really, is it possible to measure them accurately, and is it possible to measure them at scale? The answer is yes, or at least we believe that, and in fact, we have staked that on a company that we have started. First and foremost, in terms of the scale, I'm sure the community is aware of what's been happening in the world of programmable networks and the fact that you can actually get a multi-terabit switch, which is able to export telemetry at really fine time scale. So it can process hundreds of thousands of subscribers worth of traffic, and we can isolate every single flow going on, be it streaming video, gaming, conferencing, and so on. And we can actually extract very fine-grained telemetry down at the sub-second level, often in the tens of milliseconds level, that is able to reveal the exact behavior of the application. And by being able to see the behavior as shown on those two plots as examples, I've showed the pulse, what we call a pulse of a Netflix flow, and below that I've shown the pulse of a Counter-Strike game. You can actually make some inferences about not just the fact that this happens to be streaming video or gaming and this is Netflix and that's Counter-Strike, but also the whether or not this Netflix stream is working at the highest available resolution or not, whether or not the buffer, the playback buffer on this Netflix stream is healthy or it's actually depleting. So these inferences can be made. There are many academic papers that have been published on this in recent years. We ourselves have published a few. These are generally trained on data because obviously, YouTube's algorithm for serving video is different to Netflix's, is different to Disney Plus, and so on. And likewise, the games are all different. So we have, developed AI models that are able to analyze this data and estimate experience quite accurately. And we have actually built this platform, and it is commercially deployed in a few of the large operators in Australia, and it's able to show experience on an application by application basis across hundreds of thousands of subscribers per instance that we're putting in, and this is helping both, of course, the operators understand various tuning of their network, what impact it's having on application experience. And I'll just give one or two examples and stop. One of them is we have an operator who's tuning the buffers in their network because there's shaping going on, and the impact of the buffers on different applications is different. Obviously, a larger buffer helps downloads, whereas a shorter buffer helps gaming applications to reduce jitter. So helping them tune that to balance the needs of the various applications is one. And another one we are working with.
Let's try to wrap up.
Okay. So I'll just wrap up there and happy to take questions at any point. Thank you.
Great. Thanks. Any clarifying questions or comments out there? No. Then let's move on to David presenting Measuring ISP Performance in Broadband America, a study of latency under load.
You hear me okay?
Yes.
Okay. Good morning, everyone, at least from the Mountain Time Zone here. So I'm going to talk about, for those of you who recognize the Broadband America, that's the FCC Measuring Broadband America program. That's published about 10 reports now since 2011. And with Dr. Levi Perego, who's also with me on the faculty of CS at CU Boulder, we took a look at the latency under load data that's included in the FCC measurements. They actually, in the reports, to the best of our knowledge, haven't reported it in the reports themselves, but if you go to the raw data, they do have a latency under load test that they run that essentially operates when they're doing their 10-second downstream and upstream speed tests. And they send some UDP packets when that's occurring. And so we wanted to, this paper takes a look at what the data looks like. And we're just going quickly through the results here. If you want to look at a description of the methodology and the like, then go to the paper. So go to the next slide. So what this chart is showing is the downstream latency under load data by technology. And by technology, they have different ISPs that are participating in the FCC program. We selected CenturyLink as a representative of DSL, Comcast for cable, and Verizon for fiber to the home. And so you can see this is what the latency under load data look like for the last year that they reported. That big chunk in September, October, the FCC's withheld that data until they published their report, which hasn't been published yet on their webpage. And what we can see here, based upon these results, is that there's a substantial difference in the magnitude of the downstream between these different technologies. If you note, it's a bit of surprise here that the fiber to the home with Verizon is higher than cable. And we would note that in the earlier report for the data, they had pulled some of the Verizon data over concerns about the SamNose platform and its ability to process 1 gigabit per second services. So that may be a reason for that. We don't know. We're just looking at the data here and can't do too much sleuthing on it. But we see there's substantial variation by the technology. There's also, not shown here, but in our paper, substantial difference in the downstream and upstream latency under load. The average in 2020 was about 150 milliseconds for the data we looked at in the downstream, and about 350 milliseconds in the upstream. And some of this differential could be just due to the different download and upload speed differences. So let's go to the next slide. And so the last chart was the average round trip time that they measure for the latency under load. This is a plot of the maximum round trip time that they measure as well. And by looking at the maximum round trip time, we can get some more insight into the range of variability here that is possible for the network delay under the higher traffic load conditions. And what you can see here is the overall maximum latency under load data increased about 65% on average from that 150 millisecond average round trip time. And it's up about 50%. They're not showing it here for the upstream. So you can get a sense then again of this range. For the different technology types, you see here they're a little bit more bunched up, but still with DSL having a higher amount than the others. And again, the higher magnitude here can be explained in part by the upstream or by just the speeds associated with these different broadband service speeds that are offered by these different technologies. Okay, if we can go to next slide. So this is the historical or longitudinal analysis of the data, and we just focused on one ISP here. This is a Comcast, and you can see this plot of their average round trip time. And it shouldn't say 2020. Sorry, it's a typo in the title there. But you can see over time here that there's been an improvement. There's a long trend line here of improvement in the latency, about 10% every year, kind of averaged out. And recognizing that this isn't something that you can necessarily predict about how the internet performs based upon the changes in the dynamics associated with applications and the like, but you're seeing a improvement here, and the reasons for improvement are likely due to the increasing service speeds that have been occurring during this time, along with improvements in the IP protocol. So the 2020 data shown here for Comcast, and this is just for the month of November, actually includes their use of AQM and their CMTS in the downstream direction. and so you can see substantial improvement there, both in the maximum and the average round trip times, given the use of the AQM. All right, next. This is another way of looking at the data. This is the distribution of the downstream latency under load before
David,
July. Yeah.
Let's try to wrap it up because you are
Okay.
slowly running out of time as
Yeah,
well.
I can do that. That's fine. This is the last slide that I was going to talk to. So this shows the before and after. And what's interesting in this is just shows how the distribution changes with the use of AQM, and you can see how the data is most of the samples are now coming in below 150 milliseconds, so that it is good for the user experience. And with that, you can look in the paper on the findings, which basically summarize a lot of the observations that I found here, that we found here in terms of the decrease over time associated with the latency of this metric. And, you know, given that speeds, it also shows a relationship between speed and latency. And as speeds increase, we can expect over time from a planning perspective, the latencies will improve. Of course, applications will require less latency. So that's it.
Thank you. I think Jonathan had a clarifying question.
No, just question for later. Thanks.
Then we go straight into the discussion. And
sorry, Christoph, I had a super quick clarifying question, if that's okay. Thanks very much, David. This is Sam from Sam Notes here, actually. You're absolutely right. What you mentioned at the beginning, that the FCC haven't published any of the latency under load measurements in the MBA reports yet. So first, I confirm that. Secondly, you mentioned something about Verizon 1 gigabit there. In the raw measurements you're looking at, the raw files published on the FCC's website, nothing should have been excluded from there. If there's something you're missing, please drop me a line and let me know, but nothing should be missing. There are separate conversations going on around 1 gigabit and so on, but that should be completely unrelated to what you're looking at there. Hope that helps.
That's good. Again, we didn't do it kind of beyond the scope of this, and a quick turnaround of looking at the data to try to go to the next level to explain why the fiber to the home would be higher than say cable, given expectations there. And some of the earlier idle latencies that have been reported by the FCC did have lower idle latencies for the fiber to the home as compared to the cable. So thank you.
Thanks, Sam and Dave. And we then go into the discussion, and we start with Jonathan.
Okay, yes, I can add some clarification also in terms from the data set that we have from our fleet, that yes, we do see some ISPs with fiber to the home have incredibly high latency under load, which, you know, we were surprised when we started seeing people deploying our product on those types of lines. But clearly it's something to do not with the technology, but possibly with how the infrastructure is deployed and managed. But it happens, but plenty of others have excellent. Now on to Comcast and all of that, it's great to see the dramatic improvement in download latencies due to AQM, but it is important to note that even on many DOCSIS 3.1 provisioned lines, the upload is still DOCSIS 3.0. My personal line happens to be that way and still requires a local traffic manager on those to get effective low latencies.
Thanks. Next up is Bob. Bob, I can't hear you.
It would help if I unmuted, wouldn't it? Question for David on that last presentation. It's semi-clarification, but also a comment. you mentioned a number of times that latency should be better as speed increases, or you would expect it to get better, and you noticed it had been getting better. If it's a latency under load test, that shouldn't make any difference, because the flow should be given time to reach the point where it's filling the buffer the same. So it's I agree that in real life, if flows stay about the same length or don't get longer as fast as the links get faster, then you will start to see less latency under load. But I'm not sure why you thought speed will reduce latency.
Just quick. I mean, we have a scatter plot that of the data that I didn't show here, that kind of shows overall a clear, based on the data, that as speeds increase, the latency under load goes down. And I don't know if it's like the transmission delay piece, or for other reasons. We didn't have time to kind of sleuth and figure that out. But there's a clear association with that, as you see with the FCC data in general, with their idle latency as well. They have a clear trend as the speeds increase for the idle latency across all the different technologies to go down.
I don't know the details of the FCC's test, but that might imply the test is badly designed.
It could. Again, we didn't have, but to the extent, if there is something, I mean, the transmission delay obviously can go a bit faster.
We really need to get back to the queue to allow everybody to have a voice in the conversation, please.
Thanks. Dave, next up.
I wanted to point back to the second presenter's set of slides where he showed the Netflix pulse. I see that in a lot of data, if you capture it as detailed as you can. And it's one of those things that does not show up on an average, and finding ways of detecting pulses of that are really key to a better user's quality of experience. If you're interrupted every 2 seconds from whatever you're doing, it can be a quite annoying internet. Going back to the previous set of comments, as we get more and more bandwidth, the tests themselves are not running long enough to actually detect what happens for a long-running flow. So, 20 seconds proved not to be enough even 10 years ago. So I keep hoping to find passive or long-term measurements that actually run for longer.
Thanks, Dave. Omer, you're up.
I have a few questions to Johnson, so I will try to ask one or two if I have time. Question number one, it wasn't quite clear whether you're advocating for the in-application monitoring, where the application is measuring the latency data, or for in-network monitoring, where a third actor device is observing all the applications passively. So that wasn't clear. Question number two, when talking about capacity changes, have you specifically observed the effect of ISPs changing their routing from peering to transit and back? And if so, can you elaborate on that? Those are my two questions. Thank you.
Okay, really quickly, we advocate for the metrics to happen at the bottleneck point, since that's the only point in a local network, at least, where you can observe all traffic patterns and all use of capacity and the true latency at the line level versus, latency induced by things like Wi-Fi. So those metrics are what we believe are important for end users to be able to understand what their actual line quality is. So if I'm going to say my ISP is not giving me good service because my line sags every afternoon, down to 50%, then I need, the only way I can really know that is not from an application. It's going to be primarily from the thing on my network that sees all my traffic. And I'm sorry, your second question was?
My second question was regarding changes in capacity. You specifically told that we are talking about changes in capacity, and my question was, Were you able to observe changes in capacity that are happening whenever an ISP is changing their route from a peering agreement to a transit, which would necessitate completely different usage pattern of the backbone? Thank you.
Okay, yeah, our observation and all of our data has pretty much shown us that when we see this phenomenon described and reflected in that graph of the sag, that is pretty much 98% caused by local issues, bad, local loop contention on cable systems, on copper lines. It's going to be the backhaul being insufficient for the load.
Thanks. Okay, Jim, your turn. Jim, we can't hear you.
So the tests, TCP, using TCP as a testing mechanism, as Dave pointed out, means that the tests have to run a significantly long time, number one, and that's typically not been done. Number two, and so we have to question the tests up front. The other thing is that the buffering in these devices has been scaling with each generation. Because at least when there's no AQM, in order to do the single stream test, to maximize that bandwidth value, you keep TCP has demanded that much more buffering for each generation as a minimum, and memory's gotten very cheap. So while I can believe in your data set that the latencies have been dropping with time, that doesn't actually mean that the worst case, which is what really bedevils you, has necessarily changed.
Thanks. Sam, your turn.
Yeah, just more of a clarification than a question for the discussion between Dave and Bob earlier on. I think it's perfectly reasonable when you're looking at it at a macro level, as Dave's presentation did. You'd expect the idle latency to fall as you move towards higher access speeds, simply because they're using newer access technologies. So pick on like CenturyLink, for example. They're a blend of extremely slow DSL and also extremely fast fiber to the home, and a whole bunch of ranges in between, like VDSL and FTTC as well.
Jana?
Christoph, I want to speak to a discussion that's going on Slack about Netflix pulsing and so the square wave or the wave nature of traffic. This is not new. I just want to make a comment to the traffic. This is basically AVR traffic, and there's a fundamental reason why it is so. The reason it happens is because to avoid any rebuffering at the receiver, the sender sends enough traffic that will fill basically the time period over which it's playing. So for example, a duty cycle here of 50% means that the sender will send 5 seconds worth of video in about 2.5 seconds. And this is what the receiver's ABR tries to optimize for. It tries to maximize the amount it can receive, but it will typically not go close to 80 or 90% simply to avoid rebuffer probabilities. So it will reduce its rate so that it's small enough, keep it high enough that it can maximize some sort of duty cycle there, but the duty cycle tends to be 60% or so. That's what, in my experience, I've seen. And the frequency of the square wave can change depending on the kind of streaming you're seeing. This could be either live video streaming where this is much smaller. So you can have like 1 to 2 second square waves, or you can have 5 second square waves in the case of stored video. But I just want to give that's not going away. It's not going to get completely smooth. That signature is going to remain in the network.
Good, Jana. Jonathan, your turn.
Okay, just another comment around the metrics that Jim and Dave mentioned, which is not only reinforce the need to run these tests longer, but also more concurrent streams are required as you go up the capacity tiers. It's pretty easy to run, let's say, 12 streams on a gigabit download and pretty much on DOCSIS 3.0 or whatever, and just not see any latency, but hit it with 24 and you'll discover it.
Brandon?
Yeah, one question for Jonathan. There was a conclusion that you made that it's due to last mile conditions, i.e. congestion in the DOCSIS network. I'm curious if the testing methodology gives you more information that can support this. I mean, I've looked at the paper, you're showing 180 megabits per second line. For a lot of the day, you're not achieving that. I am curious if that's a function of the congestion control that's being used and it's observing very slight variations in delay and it's adjusting for that, or if it's potentially congestion between wherever the server that you're transferring from and the end user and not actually in the access network. I mean, to give a, I was on a call a few days ago with a cable provider and they claim that contention in the DOCSIS network is very rare, or in the CMTS network. So it is interesting. The other piece here is this latency under load test. Again, I'm wondering if this is realistic or representative of what users are going to see. If you're trying to fill the buffer at the bottleneck link, you know, how often is the workload that users have actually going to cause that to occur? If I increase the speed of the bottleneck link and I have the same workload, the likelihood of queuing and contention at the bottleneck goes down, and that means the likelihood that you're going to observe that type of latency is also going to go down. And that's it.
Okay. And yeah, we do see, and again, our adjustments in the dynamic range are done when the line is loaded. So we will not make dynamic changes just because a latency metric happened to come back bad. We only do it under known load conditions, in which case we know that, you know, the increase in latency is being triggered by the load. Now, could it be because of a poor peering agreement or, you know, a really bad quality peering link? Yes, it might be that, but more often than not, again, because it's seeing all of the traffic, not just a specific set, it can make that determination.
So that was Bob.
Sorry, I can't even remember why I went into the queue. Move on.
Okay, Torles?
I wanted to reply to what Jana was saying about the Netflix bursts. He said that was about the buffering in the receiver. To my best understanding, all the adaptive bitrate algorithm of all the streamers are using this to measure the downlink speed, so that for the following sequence of segments that they receive, they know what bitrate they want to receive, right? So this is a way of adjusting themselves, and the reason why they have to do this by, you know, sending unlimited speed bursts is because, you know, from the network we don't give them another way to figure out what actually the available downlink downspeed bandwidth is. So there is, you know, some argument to be made that if we had a better network service that would give some idea about the free headroom, then we wouldn't have this problematic behavior of adaptive bitrate streams, especially when you have different streaming services in the same home from different people competing with each other on their bursts.
Omar?
Oh, yeah, I have a question to Vijay. When you mentioned that you were using videos from Netflix and such to estimate the ability of ISP to serve high quality traffic, I was a bit confused because these large networks typically do not rely on ISP's capabilities as much. They just absorb the location, put their own equipment, which is completely different from the ISP equipment, and use that. I wonder, have you seen a strong correlation between behavior of Netflix, Facebook, Google, Amazon, and other services, despite that prior of having different technology? I'm quite curious how that has been seen from the outside.
To respond, or do I need to get in queue?
I think you can quickly respond.
Okay. So what we measure, and maybe it's slightly misleading when I said we measure the ISP, what we measure is the end-to-end performance of Netflix. It could equally be a bad Wi-Fi in your house. We don't know, right? What we are measuring is end-to-end, what is Netflix doing? And that pulse carries information on whether or not Netflix is working at the highest available resolution. And we detect when the resolution drops, and we detect when Netflix panics, when the playback buffer goes down and it opens more connections and tries to fetch chunks in parallel. So we have built models around the behavior, and that is letting us make these inferences. So you're right, as in it's not only the ISP who's at fault. They may or may not have a cache, we don't know, but we just measure the end-to-end performance of every stream of Netflix. I don't know if that helped.
It definitely did. Thank you.
Okay.
Berto, your question or comment?
Yeah. So the first thing is I wanted to echo what Torlis was saying, that there's a whole lot of problems around bandwidth estimation for video stuff, and this ends up presenting these patterns that we're seeing, but not only for Netflix-like content, where I'm not meaning to say that Netflix is solving a very easy problem, but it's an easier problem than solving, say, a live streaming broadcast. And the reason I say that is because the lack of a good API for measuring bandwidth actually means that we have to assert a delay in the live streaming so that we can make a buffer so that we can send at faster than the current streaming rate, so that we can actually get a probe of the network to increase the bandwidth or the quality of the video. So there's these very interesting knock-on effects that happen because of the lack of a good API from the web platform to give us the bandwidth that it sees that maybe it could look at from inter-packet delays or something like that. Lots of knock-on effects. It really sucks.
David?
Yeah, I sent out on the Slack line just some of the numbers that the FCC reported earlier in their data last year on the different ISP type, technology type. But I think this question of what's the long-term trend here on latency and the performance is important for kind of understanding it, putting the right context for different improvements. And if we don't have an agreement on the metric in particular, that's very important. If the FCC has a 10-second test and it should be 20 or 30 seconds, that's an important thing to communicate out, so that we can get, because we know speeds are increasing. We're at 1 gig, we've got XPON going to 10 gig. So do we anticipate improvements or not? I didn't mention it, but the AQM that Comcast implemented was basically a 50% improvement year on year for the month of November. Now that, again, I understand that you can't just take that to the bank. It's, that you can guarantee that type of improvement. But, if as these protocols improve, there can be some expected improvement in performance over time as the service evolves. And I think that's an important piece of calculus to understand how this problem the consumer experience problem is going to evolve over time.
Thanks. Jim, your turn.
It's very important that people stop looking at applications in isolation, particularly since we often have asymmetric bandwidth between uplinks and downlinks. It is often or usually the case that it's some other application / person who is doing you in. If you screw up the round trip times in the upstream direction, it makes it real hard for the downstream to figure out how to buffer your video, right? And our applications are changing. The resolution of our video streams is going up. The amount of image and video content that people upload or want to backup keeps going up. Yes, I first ran into this phenomena with downloading large things, but the upload is now more and more common as the applications are there to really exploit the network. So stop looking at a single application. Look at how the applications are affected by other applications trying to share the same network.
Jana?
Thanks, Christoph. I actually want to echo what Jim said. I don't think we should be over pivoting on Netflix. I mean, there's a lot of applications that have many different behaviors, and Netflix's behavior is not irrational, right? I mean, they're doing something that is solving a particular problem. It's not specific to Netflix either. Let's be clear about that. This is ABR video in general. You might see some pronounced effects with Netflix, but it's going to be there as long as you have ABR video doing this capacity probing thing, bandwidth probing thing that it keeps doing. And to Torles, to your point of this is not. These are basically continuous testing. That's hence the adaptive in ABR. It's not just done at the beginning of a stream. You can't just ask the network, hey, what is your bandwidth, and then start streaming at that rate. It is a continuous measurement that's happening. We basically have to do online measurements. We don't have a way of simply querying and finding out what the bandwidth of the end-to-end network is. So that is a real problem here. I mean, there's a practical engineering problem here that they're trying to solve. It's not out of nothing. And I think Jeff made a point earlier that maybe we should engineer the network around this. To that point, I'll come back to maybe something that Jim was noting, but I'll note it anyways, that having some amount of isolation across applications, having some way of allowing these. Jim, I didn't say anything that bad.
Sorry about that. I'm trying to get it turned off.
It's all good. Yeah, that's all I had. I said my last point is that being able to isolate applications from hurting each other is a potentially useful way of thinking about this rather than trying to change every application on the planet.
Thanks, Jana. Vijay, you're up.
Thanks. Yeah, I think good discussions, and I'm also looking at some of the comments in Slack. I think the key point is, and that I'd like to reiterate, is by looking at the behavior of any application, and Netflix was just an exemplar, and you have YouTube, you have Prime, and we can build a data-driven model of how it behaves, and that can be used to estimate experience. Of course, you'd have to do this across many applications, not just one called Netflix. And Sharat, my PhD student who's also on this call, has done that extensively for games as well. In fact, the top 100 games on the Steam and the Twitch charts. And there's a lot of variation, TCP games, UDP tick-based games, non-tick games. So it's laborious, and but it definitely does have its rewards in terms of the meaning it provides to end users, because even Call of Duty is different from Counter-Strike, is different from FIFA, and so on. So really getting down to an application by application level is rewarding, even though it's fairly hard work. So I just want to reiterate that point.
Thanks. Jeff?
Sorry, unmute. I'd like to make the case that actually we should pivot and we should think long and hard about video streamers. I lived through an age where we spent a huge amount of time engineering for VoIP, when it was marginal both in terms of traffic volume and, most importantly, totally marginal in terms of ISP revenue. We were spending a huge amount of time for basically minute marginal pieces of traffic. Video streaming is 80 to 90% of the traffic we pass across this network, and I would actually posit it's around 95% of the revenue. So yes, of course we should pivot. That's where the money is. Thanks.
Thank you. Torles?
To get back to what Roberto was saying about real time and this bandwidth probing, right? So I think everybody has seen that when you start a streaming video, then the quality slowly ramps up, right? And that's certainly something which you don't really want to have in a real time video conference when you're starting and stopping to send video, like in a multi-party environment where your stream is not always on. So we're kind of having the problem of the TCP slow start and any other bandwidth probing of new flows. And so there are a bunch of other things that go into the codecs, like increasing, decreasing FEC, but ultimately when you give up bandwidth, you have to get it back afterwards. And I think that's the most difficult thing that I think we can't improve on unless we improve the network service itself.
Thank you. Omar, your comment?
A comment to Vijay. I wonder how long, very general, does it take to develop a model because that would match the behavior of a particular video provider? Because if, for example, let's say Facebook is running 5 different experiments and is gradually shifting it, I just imagine that it would be quite hard to adopt the model in the almost real-time rate to accurately track the experimental location. I just wonder whether we have any thoughts.
Absolutely. I'll give you a very short answer, and a longer answer Sharath can give maybe offline, which is that luckily providers, the major providers like Netflix have nerd stats. And if you know how to enable nerd stats on your video, you can train a machine to automatically harvest the ground truth in addition to what it's seeing on the network. And the training becomes fully automated. But not all providers give you nerd stats. So it can be more laborious and manual for the other providers. But Sharath has a lot of detail on this.
Thanks, Vijay. Just as a comment, I closed the queue, so there's Brandon and Jim coming up. Brandon, your question or comment?
I think it's a good point that we shouldn't constrain what we consider in terms of measuring QoE too much to any specific set of applications. At the same time, as other folks have mentioned, the vast majority of internet traffic is now video traffic. That's typically going to be served by CDNs that are local to the user, which means that transit networks are not going to be involved. Sometimes those CDNs even have nodes co-located inside the end user ISP's network. And then that video traffic is going to be a continuous cycle of the player requests a chunk, the sender dumps it into the network as fast as possible based on its congestion control algorithm, and then the receiver requests another chunk, and the process just continues to repeat based on the receiver's buffer. The other things you're going to have is image traffic. That's going to be similar. I'm loading a web page. I'm going to quickly request as many images as possible, get them served to me so I can display that page. And then you have constant bitrate traffic. That's kind of like what we're on for this call. There's my voice right now has to be carried to you. There is some constant bitrate encoding of it. The video can change, but in general, we need this traffic to be constantly delivered. But it is none of these types of traffic are representative of me downloading a large file. And that's what we typically see when people are developing congestion control algorithms. Those are the types of experiments they look at. If I have 2 senders or receivers, they are both sending this large file. How do they share bandwidth? But that's not as representative of the actual traffic that's on today's internet. Thanks.
Jim?
I will push back very strongly on the idea that the only kind of video traffic that's important is things like Netflix. If the pandemic has taught us anything, the lifeline for our children has been, terrible as it is, remote education via systems just like what we're using right now. It's important. We must engineer a network that is good for all applications.
And thank you. So we move on to the second part, metrics number 3. Let me start sharing the slides. And we start with Kyle on Beyond Speed Test, measuring latency under load across different speed tiers.
Sure. Thank you. Hi, everyone. My name is Kyle. I'm about to be a second-year grad student at the University of Chicago, working with Professor Nick Feemster. And today we wanted to share some preliminary results from a measurement study that we're conducting. Next slide. So we're about to deploy about 100 devices across homes in Chicago to measure certain aspects of the internet that people receive. And before this, we've had a bit of a beta deployment to 11 homes of the members of the group and the lab to test that the system's working and validate that the results we're getting are reasonable. And we've been able to make some pretty interesting observations from the data collected off our latency under load test. And before I get into that, I just want to give a little bit of context or explain how we're running the latency under load test. And so we first saturate the link using an IPERF3 TCP speed test, and then the latency under load is given by the RTT of an ICMP packet sent when the IPERF3 test is running. We run this test in two phases. First, when the uplink is saturated, and then when the downlink is saturated. The test is run every 2 hours, and the devices have been installed for at least 30 days, so we have a decent chunk of data to go off of. Next slide. Now, our first observation may not be that surprising, but it's that latency under load is related to speed tier, subscriber speed tier. And what I mean by this is that users subscribe to internet service plans with lower throughput generally experience higher latency under load than those on higher speed plans. This trend is much more observable when you go from those on the 110.5 plans to the 400 plans than when you go from the 400 to the gigabit plans. We've included this plot in the paper, but you can see what I'm talking about when you look at the latency under load jump between the red trend line, which is the 110 subscribers, all the way down to this group at the bottom, like the green and the orange trend line, which are almost stacked across each other. Next slide. And our second observation may be a little bit more surprising, but it's that users subscribe to the same service plan, to the same speed tier, on the same ISP, experience pretty different latency under load. The devices that we've deployed so far are deployed in different neighborhoods. And looking at the figures on the right, first at the one in Hyde Park, you can see that one subscriber experiences nearly consistently higher latency under load than another. Same observation can be made about the two subscribers in another neighborhood, South Shore. And on top of this, the subscribers in South Shore experience nearly at least twice as high latency under load than those in Hyde Park. And just to reiterate, all of the subscribers in the figures on the right are on the same ISP and are all subscribed to this ISP's gigabit service plan. And so we wanted to bring these results to this workshop and get some feedback from the group, because while the differences are clear, the causes are not. So any feedback about our methods or suggestions as to how to narrow down the potential causes would be very much appreciated. Thank you.
Thank you, Kyle. Matt, did you have a short clarification question?
Yes, I want to know if you had any provisions for bad echo here. Qualifying the subscribers' gear, whether the subscribers had the same or different equipment.
They would have different equipment, but we know what equipment they do have.
Does the data bend by that?
Excuse me?
Can you separate that out as a possible confounding factor in the data?
We can. We haven't done that for this yet, though.
Thank you. Jonathan, another question or comment?
Clarifying question. Is the detecting device cascaded from the ISP supplied modem and router?
That's right, yeah.
are the models different between those two data sets that you present in the slide that's up?
When you say, what do you mean by model?
Are the exact same brand and model of cable modem?
No, so it is likely that they're not, but let me put it this way: they're not, but a lot of them are. Like a lot of them get the cable modem box from the ISP.
Yeah, I'll just point out that, let's say I've seen that exact sample. My guess would be one of those has a Puma chip, the other doesn't.
Thanks. Jim, one last comment or question? Jim, we can't hear you.
The device, the cable modem and the like matters. The devices in it and the amount of buffering in them vary from model to model, and you should bin according to that.
Okay, that makes sense.
Thank you, Kyle, for this presentation. We now move on to Gregory on error performance measurement in packet switched networks.
This is a multi-party contribution, and let's move to the next slide. So what motivated us, often in our discussions, we use characteristic as availability, path availability, service availability, and got to wonder is what do we mean, and how can we measure, how can we express this if we want to use it as a metrics. Next slide, please. So error performance. OEM tool sets include methods that help us to detect network defects and measure performance. Defect can be characterized and is inability to communicate. In packet switch network, so the loss of path continuity, inability to get packets from one point to another through the network can be equated to 100% packet loss. So that's how, from the fault management OEM, we can hop to the performance monitor. And if we look at the packet loss in fact is packet that's been delayed infinitely. So it's infinite delay of a packet. Error performance is a quantitative characterization of the network condition between endpoints that takes into consideration defect and their performance. Next slide. So we believe that error performance measurement is active OEM in terms of it can be in packet switch networks specifically. It can be measured using active OEM measurement methods according to classification in RFC 7799. And it's not a new, it's well known from concentrate media like PDM, and it's based on guaranteed presence of data. So the data is anticipated and expected by the receiver. In a packet switch network that is based on statistical multiplexing, that cannot be achieved unless we use periodically transmitted probes, test packets. So the active OEM can create a characteristic subflow that statistically can be correlated with the behavior experienced by the data. Next slide, please. So looking at what's been achieved and used for PDM, we look at several parameters in error performance metric, such as error interval, severe error, and error-free. So these intervals, they can be combined in the periods as availability and unavailability of what's being monitored instance. To make it stable, this periods has to have a certain number of consecutive intervals. So we don't want to have characteristic that changes each and every interval. So because of that, we use the same logic and method defined by IETU to have 10 consecutive periods that constitute, but we are saying that this state, availability or unavailability, had started from the beginning of this consecutive intervals. As a result, other metrics that can be used as a error interval ratio and severe error interval ratio. You will note that we do not characterize the specific requirements for the packet loss ratio or delay variation. That can be specific to the object that's being monitored, to the instance of the service of the tag. So the thresholds can be altered and adjusted, and that because different services, different paths will have a different requirements and in terms of their tolerance to packet loss and packet delay. Because there are several protocols being developed and in IETF, for example, that's where we do this work primarily. We are coming with a proposal that helps to integrate fault management and performance monitoring OEM in one integrated IP or packet oriented layer 3, layer 2.5 protocol that combines best qualities of BFD and performance monitoring tools. Okay, I believe this is our presentation. Any questions?
Thank you, Greg. There's nobody in the queue for any clarifying questions, so we move on to Gino and focusing on latency, not throughput, to provide better internet experience and network quality.
Thank you very much, Christoph. So before I start digging into the slides, I want to set a bit of context. I'm a little bit of an outlier in this workshop. In fact, some of you guys may even think of me as the bad guy. And as honored and excited as I am, it's a little bit difficult not to feel a bit of the imposter syndrome. But I'm hoping I can bring you guys a bit of a unique perspective. I don't do PR&D. I don't sell anything. I'm not part of a product group. My job really is to apply everything that you guys are bringing to the table here and make it relevant to the end users. So for years now, I've literally spent my days working with the whole ecosystem, the SOC vendors, the CP vendors, the platform, the web scale, the CSPs, the CDN vendors, gaming studios, you name it, all around improving the quality of experience of the end user. So I bring a different view. You guys are the metric experts, and on all my friends at Apple, Google, Bell Labs, but my job is really to understand how to make this relevant to the end user. So when you guys come to me with, I got this new queuing algorithm, I'm like, great, how's going to help that my kill debt ratio? And if you look at me with blinking eyes and you know what I'm talking about, then nobody's going to buy this stuff. So don't get me wrong, I work extensively on queuing, traffic optimization, but my focus is really to understand how to translate this into something the consumer understands, wants, something the CSP can sell, the CP vendor can integrate, and the SOC vendor is willing to do. We heard some amazing comments from Stuart, Jana, VJ, Jim, and so many others on the real world benefits, and I love that. So residential internet used to be a best effort. COVID changed that. I think, Jimmy, you were mentioning that earlier. I totally agree. People don't just need it. It's a basic human right in a sense. You rely on it for critical services, work, education. So what I'm going to share with you guys here is understanding how we can solve that potato in the microwave quote that came out a couple of times. I love that. There are ways to detect when there's a potato in the microwave now. We've opened up the CP environment via containerization, and I'm working with a whole bunch of you, actually some of you that are here, on deploying agents in the CPEs that will give you that low-level access to the queuing, Wi-Fi, WAN, RAN, whatever you want. So no longer you're gonna have to infer measurements, you'll be able to get access to it. So with that said, I'll go quickly to the slides. I want to share some real world results. I like using the cloud gaming because it's a great example of high bitrate video, constant video with low latency. And the reality is, as has been said, 90% of your issues are going to be in the home or in the last mile. There's a lot that you can do to focus on metrics and improvement, but you're hitting a point of diminishing return if you don't focus on the in-home and last mile. That's really where things matter. Next slide. So what we've done is we've actually gone ahead and done some real world measurements. When I say real world, we're talking to residential homes with real gamers, pro gamers, amateur gamers. And I remember a tier 1 operator saying, you know what, we have a fiber network, yet people complain about our gaming. And so they're like, well, our ping tests are great. And yeah, if you look at the lower left graph, their ping times for that cloud gaming service with NVIDIA was great, 62 milliseconds on average. But you can also see the inconsistency because of the in-home network and Wi-Fi and everything else. And every time you see those little spikes, that gaming session, that video conference was severely impacted. When we applied things like Pi-square QM and L4S, again, same households, same real-world users and everything else, you saw a dramatic improvement in the quality of the experience in the end user. I don't really care that the ping time improved from 62 to 43 milliseconds. That's irrelevant. It's a consistency, that deviation from the mean, that really matters. And for me personally, I had to be able to understand that, I had to get involved. I play games. I'm a Twitch streamer on Friday and Saturday nights, and I saw my kill death ratio increase by 0.5 in 4 weeks. This is what is going to drive the consumers to force the service providers to pay attention and to buy into this stuff. Next slide. We also did the same thing for video conferencing. So with a partner of ours, Domos, and I thank them for being able to share the stats, we did a video conferencing using the same technology, using real world enterprise customers, a worldwide global consulting firm, if you will. We took some measurements now on video conferencing over time and being able to understand how, by focusing in the in-home and the access, in this case, it was a 5G RAN, could we improve the video conference? And we did. We provided some really amazing results where at the 90 and 99 percentile, where is really what you want to focus. If I have one video blip in a half hour, that's enough to enrage me if I have 8 hours of meeting, and that happens every hour. So for us, it's not the 50th, it's not the median, it's that 90th and 99 percentile that we really want to focus on. And be able to show that you focus in that last mile and the in-home, you can have significant improvement here. And you know what? I don't have a bet in the source if it's Pi-square versus another algorithm. What I care about is, will this translate into something the end user can feel and can want and is willing to pay for it? Next slide. And in this case, if you can go through, yeah, exactly. So we want to focus on tangible real world benefits from the consumer point of view. Consumers don't care about CDF curves. They care about KDs. They care about FPS. They care about all of these things. Everybody said it already. All my thunder has been stolen for the last day and a half, but that's great. Now speed tests have reached its end game. We can already provide 300 times more peak capacity than the average sustained usage from a broadband sub. So if you have a 500 megabit connection and you have gaming issues, you have video conferencing issues, going to 1 gig or 1.5 gig is not going to solve any of that. The consistency issues also aren't from the general internet. They're largely confined to that last mile in home. There's a reason 70% of all the support calls that come to a service provider are Wi-Fi related. That's the reason. They don't care. They don't call to complain about Netflix. They don't care to complain about this. They care to say my Wi-Fi is bad. And platform and web scale providers, Apple, Google, Netflix, a whole bunch. They've been, I give them credit. They've been trying to work on this for many, many years without implicit support or help from network. But today's networks, the service providers and the CPEs are capable and ready to support this. Next slide.
Let's try to.
Yeah, I'm just gonna finish up with this one really here.
Thanks.
Is I did the consumer surveys. The consumers are willing to pay for better latency, for their own controlled latency. 70% of the population is willing to pay from $5 to $20 a month. And over 65% of them want the ability to tell the latency agent, if you will, what is important. Is it gaming? Is it streaming? Is it in the morning? Is it in the afternoon? Even the service providers, the NPS score increase when they give that ability. So last slide. So with that, I guess what I'm saying, the tool are there, the technology is there, all of the ecosystem partners are willing to take this on. So just give me a buzz. I'm willing to connect the dots and help out here.
Thanks. We have two clarifying questions. One from Sharat first.
Sure.
Hi, Gino. I think a very good talk. And these are some of the problems we've seen operating as Canopus networks and ISPs as well. What would you think is the point at which we need to intervene to help alleviate some of these issues? Was it the home router right within the household premises, or was it the CPE where typically ISPs enforce, the bandwidth plans or
Definitely
other
the CPE. Yeah, definitely the CPE from an historical perspective. It was always a cost at the bottom. CPEs was give me the cheapest thing I can put in the home that gives Wi-Fi and that will, that I can manage. That's changing. The CPEs are not a cost anymore. They're a way to differentiate. They're a way to create value and to monetize. So that's changing. You can't go and replace everything that's in the field, but there's a different mindset that the service providers are bringing to the table now.
What about BNGs and where do they sit into the context? Because they are the shapers essentially.
Oh, yeah.
At least that's how I know in Australia's context.
Let's take that offline because that's a whole conversation itself on BNG, virtual BNG placement. That's going to take us half a day.
All right, thank you so much.
No problem.
Okay, thank you, Gino. That moves us on to the next presentation by Praveen on transport layer statistics for network quality.
Hello, everyone. So I'm going to talk about the state of the art of transport statistics. I'm also going to talk about some of the challenges we face today in using these transport statistics to gather network quality information, and some challenges and ideas where IETF could play a role in making this better overall. Next slide, please. So why the transport layer? So the transport layer has very good visibility into performance metrics. So for example, RTT, which is latency, loss information from the network, reordering, bandwidth estimates. So the transport layer has really rich information. With the encryption at the transport layer now, particularly with Quick, it is also the right layer to expose this information up to the applications. Because the visibility in the network is reducing compared to TCP. And assuming ideal apps in terms of not having bottlenecks in putting enough data out on the network, the transport layer basically determines what the rate is due to congestion control algorithms, flow control, pacing, bursts, and various other mechanisms that are usually part of the transport layer. And by correlating these metrics with application layer metrics, we can have a very rich idea or very rich picture of why there is increase in tail latency or why certain requests are taking longer. So in terms of what is being done today in platforms, we have APIs that are exposed in the form of eStats or like TCP info, which can be used by applications to gather this information. One of the challenges today is that this is poll mode, right? So the application needs to query this information periodically. One of the enhancements here could be push model because the transport does know when significant events happen. For example, congestion or, a stream gets closed or, the connection ends unexpectedly. So there are cases where the transport could push this information to the application versus it being the other way around. And Quick introduces a little bit more complexity because some of these statistics now become per stream, which means we need to expose way more data depending on how many streams the application has opened. So the amount of data that we're dealing with increases compared to like TCP. So what do we correlate with? So the application layer has their own level, they have their own set of metrics that they measure to determine, for example, what the effective user experience is based on, say, response time, request per second, delivery rate, jitter, etc. And being able to correlate this sort of transport layer data is extremely useful. One of the problems we see is with connection reuse. So if the application layer reuses a connection, how do we exactly correlate the statistics that are associated with a particular request down to the right connection. And we also have problems with multiple streams, right? So how do you exactly correlate that your request went on a particular stream and the bottleneck was due to the stream's behavior, let's say flow control? The other interesting idea here is also like support for statistics difference, basically being able to timestamp when a request starts and ends between the application layer and the transport layer, and being able to extract just the right amount of metrics that are associated with a particular request. Next slide, please. So what are the challenges in using transport layer metrics? So one of the big challenges is it's a multi-platform world, it's a multi-transport world, particularly with Quick. Now there are like so many different applications. So the reason this is a challenge is because typically you don't want these metrics from just one side of the connection. Typically you want data from both sides because there are cases where the performance could be limited by, say, flow control on the receiver. So and the receiving application as well. The other challenge, I would say, in the cloud world is different administrative domains. So if you want to extract this information, you're not always the same. It's not the same application running on both sides. It's not under the same administrative domain. So there are like privacy issues in terms of what sort of data can be exchanged between the peers. And that the other problem also is that if you do this, try to do this in a general way versus application specific, there's certain information that is not available today. Like what was the application intent? This is not always expressed in APIs and somewhat difficult to infer. And the user intent is also not expressed. Like the user may choose that a certain application is actually low priority at the moment, right? So let's say you're in a video conference and you're downloading files, you want the file download to be like a lower priority. It's not always explicitly expressed. It's quite difficult to determine what that intent was. There are cases where there are system services, for example, like an operating system updates, where it's very it's very easy to infer what the intent was. But if it's a user controlled action, it's pretty difficult to infer that today. And the receive side transport has less visibility, so another reason for why you want to exchange this information in some form. So some ideas where I think the IETF could help is some application layer mechanisms to exchange these transport metrics in a privacy preserving form. This would be extremely useful given all the challenges that I talked about before. API improvements, of course, we've had the TAPS working group, but basically, how do we express application intent? How do we infer user intent? Some of these are like extremely useful research areas. And then in terms of like measurements, there's passive measurements and active measurements. Both of them can yield very rich transport information. The question is how you sort of like sample and pick between passive and active measurements, because with active measurements you may not be measuring the right application behavior. So, and that's all. Thank you.
Thank you, Praveen. Are there any clarifying questions to Praveen specifically? Otherwise, we can move on to the discussion section. And we start with Michael.
All right, that is a follow-up to Praveen. Just because you mentioned the TAPS working group, I cannot stop myself from asking what specifically would you like to see that we don't currently have in the API?
Yeah, good question. So I do think the API is right, but the problem today is that there is already like, HTTP APIs, for example, that are quite entrenched. It's not just like new applications that can write to a new API. It's also like existing applications. So I guess like, it's a platform challenge to both have new APIs where applications can adopt and also being able to infer that, right? So I think that's where the challenge is. What do we do with all these existing applications that do not express intent today?
I agree with that.
Next up is Jonathan.
Okay. Yeah, quick question. Instead of inferring, I haven't heard that much discussion about requiring applications to actually use marking using DSCP. So if you're going to do background downloads, mark it CS, with the right DSCP marks, and just the same as like my WebEx app is now marking my video and my VoIP correctly. I don't have to infer anything. It's telling my router which tins to put the stuff in, and it's going there.
So maybe I can bring a quick comment on that one, Jonathan, is from my experience dealing with the hundreds of carriers around the world, many of them today will still sanitize or whitewash those markings coming in from home. So even if you had the applications do it, there's a very good chance they'll be sanitized before they leave the CP anyway. So I think there are ways to do it in band without using the DCP markings, and there's some cool ideas that I've been working with. Unfortunately, that approach, as much as I like it, don't get me wrong, I'd be totally in favor for it. Unfortunately, a lot of the providers are whitewashing those or sanitizing those markers.
Response on that was just basically to say, local prioritization at least might respect it. I hear what you say about ISPs.
Through the CP, correct. Yeah.
And that's where the problem is.
Yep.
So it is useful.
Thank you. Stuart, you're next up.
Thank you. I have a comment or question for Kyle. When you are measuring the latency on different access technologies, I'm interested in the challenges of measuring gigabit, because if I actually have gigabit service from the ISP, I probably don't have anything faster than that in the house. If my computer is connected by gigabit Ethernet to a 35 megabit uplink, it's pretty clear that the bottleneck is in the cable modem. But if my cable modem or my fiber is going gigabit bidirectionally, then when you're measuring latency under load, you may actually be measuring the buffer bloat on the device itself that's sending. Buffer bloat in the Ethernet driver, buffer bloat in the Wi-Fi driver. So at that point, you're not measuring the ISP equipment anymore. You're measuring artifacts of the testing device.
Thank you, Stuart. Kyle, did you want to reply?
Yeah, I just wanted to ask if you had any, is there any way to avoid measuring just the devices other than just making, we can't ask people to upgrade their infrastructure at home, but maybe if we do stuff in lab, we can control for those things.
It's just an observation that when you're presenting results, right now, presenting meaningful results for gigabit is hard. We've had gigabit Ethernet on laptops and desktops for a decade, but it's rare to have more than that. There is typically one bottleneck on the path where the buffer forms, and that's what you want to measure, and that's the slowest hop on the path. When your laptop becomes the slowest hop on the path, now you're dealing with the vagaries of the Ethernet driver or the OS on that device. So until we have 10 gig widely on laptops, measuring ISP performance at a gigabit and above is going to be hard.
Gino, you're next in line.
Yeah, so on the Stuart on the gigabit, that is absolutely a major issue, especially in the last 5-10 years as gigabit and 10 gig speed have come on. There's not a lot of CPEs out there that have the inbuilt capability to do that kind of user space line rate testing. So we've been forcing a lot of the SOC vendors to implement hardware acceleration so we can do these kinds of tests, but they're not really prevalent today. So I like the angle that you said that the end device, PC, smartphone, whatever it be, may have the trouble doing those kind of line rates. But even the CPs themselves from the service provider may feel struggle there. A lot of the low end ONTs and CPs don't have the SOCs that can do that kind of line rate. But that's changing. We're forcing that. We're seeing Qualcomm come out. We're seeing Cortina, offer IPERF3 hardware acceleration, so you can do 10 gig line rates and these kinds of things. But that's not going to change overnight. For the largely the population today, that's still an issue.
Thank you, Gino. Robin, you're up.
Yeah, I wanted to say that it seems that what Praveen was saying has a huge amount of overlap with what I will present in the next session. About being able to merge application and transport metrics in some way. I wanted to say that our solution that we propose for the API problem is to bypass it and just have each layer export metrics or information by themselves and then do post hoc merging. via different systems. That kind of translates the problem into how do we sync or correlate these things there. But maybe that's a bit more tangible or feasible in the short term. And then another challenge that we identified that I don't think you mentioned, Praveen, was once you have these shared or merged metrics, then what? Then you suddenly need new tools and new data mining techniques to actually find the correlations between is what's happening in the application visible on the transport and vice versa. And that's we have some experience with that now with Quick, but that in my experience is even a bigger challenge than just combining the data somehow. Thanks.
Thank you, Robin. Praveen?
So yeah, I think I have 3 comments. I'll try to be short. So on the DSCP marking, yeah, I think like it's also gamification problem, right? The platforms still need to sort of make sure that applications are not just cheating by trying to get the best quality of service. I had another comment on Robin's question. Yeah, I think like the correlation problem is hard. We do have applications at scale today that are doing this, like particularly at the tail, like you zoom into the P99 and you look at those requests and the associated transport stats. So it's doable. There are challenges though, yes, because it does require some manual analysis today. And then I have a question for Gino. So you were talking about users are willing to pay for like lower latency. The question then is like, if I'm paying for that, then I would need some sort of like proof of the fact that I'm getting a better service, right? So how do you, what are your thoughts on like being able to demonstrate that?
You're absolutely correct. So the first thing is you need to prove it to the service provider. So right now, that's why I said like you got to care about what the end user does. If he's a gamer, he's going to care about FPS, kill dead. He's going to care about all these things. So we do real life field trials to be able to show with real gamers at the service providers what this does. We do the same thing with video conferencing with enterprise. Once we're able to show the value, NPS scores increase for enterprise, gamers are willing to pay for it. No, give me $10 a month so I can get 2 more kills. Once we have that and you give them the tool, you got to give them something that the end user can see. If there is a potato in the microwave, tell me that it was a Wi-Fi issue that it was causing the lag. I'm okay with that. So you need to be able to isolate, where the spikes come from, the buffer flow comes from, or whatever. But you need to be able to convey that into the terms of what they're going to sell. The service provider is not going to sell latency. He's going to sell you a gaming package. He's going to sell you a working from home package. He's going to sell enterprise services. So whatever you do has got to be into that context. What is the end user of those services looking for?
Thank you. Next up is Alex.
Yes, hello. Yeah, I have another comment also to Praveen, which also ties a little bit also into this. So I think and this concerns actually the application intent and the comment about basically prioritizing, saying what traffic is more important, what is less important potentially. I think there's also a case to be made to prioritize between different metrics and say basically for certain applications you want to have, well, which trade-offs are you willing to make? It's easy to say, oh, this is really important, I want to get better service, but what is more important to me, right? Am I willing to sacrifice or trade off my latency against loss, against the possibility, for instance, of loss? Do I want to have the trade-off the other way? So to have this also a little bit, so it's a more dimensional, I guess, than just having better quality is one dimension. That there are more trade-offs there. So that's, I guess, both a comment and the and the question.
Absolutely. I think like that's why I called it a research area, right? So, and in fact, some applications might want to like be better citizens on the network and say, hey, this is my max data rate. I'm willing to trade off some data rate for, let's say, low jitter. So yes, this would be expressed in terms of like trade-offs, and there's more than just priority, right? So, you could express this in terms of bandwidth caps, like, latency requirements, jitter requirements. So yeah, this could get complex. I absolutely agree.
Thank you. Matt, you're next up.
I have a question about report scoping. Most of us here are measurement oriented. But there's actually this comment about bleaching and the problems of bleaching QoS. One wonders if there are perhaps some statements we should make about infrastructure that bleaching QoS in fact causes problems for all sorts of people. and whether or not that kind of statement would be in or out of scope. If it's in scope, there's a slippery slope, because there's a lot of things that people would want us to say, a lot of people in this group that would want us to say that might not be totally consensus. And because it's very hard to say things like you want to do something that resembles AQM without saying which flavor you want to use, for instance. So I don't know how to deal with that, but I think it's actually an important question that we should address fairly early on in terms of what we prioritize some of our talking about.
So with respect to, if I can interject really quick from a process point of view, with respect to the workshop report, we absolutely can put in anything that we feel that we do have, consensus about, or even, state that some people think that this type of problem exists. So if you guys want to talk about bleaching and the problems with it, and the fact that, I think documenting industry practices that are getting in the way of things that we want to do in terms of defining quality of service, there's nothing wrong with doing that. We do have to be, of course, careful about the wording and not call out names and and document where we may not be in 100% consensus, but we can absolutely do that.
I guess my question is, should we do that?
I'll leave that to the group.
To the queue then. Jim, you're up.
I have 2 quick points. Hardware accelerators are not a panacea. They often result in more and more hidden buffering. So beware of that. The other thing is that we're in this bandwidth race. We have been for eons between what Wi-Fi can provide and what the backhaul provides. So, in fact, our bigger problem is usually in Wi-Fi. There, it's getting the SoC vendors to invest in cleaning up device drivers is the biggest thing, along with the platforms themselves. I don't know what the state of Mac and Windows are doing. Linux is mostly cleaned up. So that bandwidth race is a historical race. I expect it will continue. That also means that the platform is involved. It's your operating system that has what we found at least half a dozen different places inside the Linux operating system that we're doing buffering in the network stack. I do not know what the current state is in other platforms, but I wouldn't be surprised. And the device drivers are where our big problem is left in Linux. We only have a few Wi-Fi drivers that are good. I can go around doing a backup simultaneously with video conferencing over Wi-Fi. I don't think very many people on this conference call can make that statement.
Thank you, Jim. Björn, your turn.
Yeah, first I'd like to say I completely agree with you, Jim. That's a good point. And then this discussion about the latency under load tests and how it may be hard to run the test long enough or be able to generate enough traffic to actually get the results that you want, because you want to measure sort of the depth of the full buffer at the bottleneck link. It sort of points to an issue with that test, because it gives you the worst case performance in a sense. But when it discovers that the performance is not what you want, it doesn't tell you where the problem lies, right? So I think a really important feature of a metric to solve these issues is that you need to be able to measure at intermediate points, or to subtract one kind of measurement from another, so that you can isolate, is it A to B or is it B to C? If you measure A to C and you get a negative result in the sense that performance is not good enough, is it the A to B link or the B to C link? If you can measure A to B by itself, or if you can measure both A to B and A to C at the same time and then do a subtraction, then that allows you to solve that problem.
You can't subtract because the bottleneck is switching back and forth potentially at a high rate. because
Sure, but
because wireless is a share and Ethernet are shared media.
Use the queue, please.
Let's go. Thanks for the comments. Let's go back to the queue. Gino, you had an answer to Stuart's gigabit comment. Do you still want to
I'm
comment on
good,
that?
thank you.
You're good on that. Cool. That brings us to Stuart. Stuart.
Thank you. I wanted to comment a bit more on the gigabit. I kind of think it's pointless measuring gigabit because 100 megabits is enough for 2 4K video streams and WebEx and sending email at the same time. An observation I'll make is if your ISP service is 100 megabits and your Wi-Fi is 200 megabits, then the queue is in the cable modem or the CMTS. And if they're managing the queue competently, you can have low buffer bloat. The irony is that if you upgrade your ISP to 500 megabits or gigabits, now your queue is almost certainly in the Wi-Fi access point. And if that has a dumb, bloated FIFO queue, that's not the ISP's fault now, that's your Wi-Fi access point. So upgrading your internet service can actually give you dramatically worse quality of experience because the bottleneck moves somewhere else.
Comcast did that to me personally.
Thanks, Stuart. Charles?
So to answer to Gino's, I was very positively surprised about that data of customers willing to pay money for lower latency. I'd really love to see some more data on that and collection of examples, because the only one I ran across is rather old, and that was in Germany when in the DSL network they were offering lower latency for the FEC in the ATM layer of DSL. I think from 20 millisecond down to 5 for €5 a month, and that seemed to have some success, but went away with VDSL. So I haven't run in consumer service, especially for gaming, any other data points. So that was very interesting. The other point about the bleaching, I think that the DSCP isn't really good as a standards mean to convey the type of policy differences we would like potentially to see, like flows, wanting to be faster than other flows. We do know that we can do that with congestion control in waiting fashions. There are no standards for that in the DSCP, so those would all be proprietary or specifically configured by service provider that want to support anything like that. And just passing the DSCP along, of course, also has problems. So it's a quite complicated topic.
Thank you. Dave, you want me to show the slides?
Yes, please. I wanted to go to the second presenter's slides, that wonderful breakdown of where we find latencies and bandwidths jitter. I have a very similar slide that I've been using for ages, and that's some of the depth of the problem. I believe Stuart pointed out that we also have serious difficulties on the hosts themselves at higher rates. Kind of argue with the overall jitter potential in-home Ethernet and in-home Wi-Fi. I've seen over 7 seconds. DOCSIS has gotten a lot better, but it is wonderful for us to try to, can we all agree that this is the kind of classes of problems and where they happen in the network? The part that I wanted to talk to specifically, however, was, can you go to the next slide, please?
Sure.
Thank you. I'm really glad you don't have a horse in this race. I do. There are thousands of routers with vastly improved Wi-Fi performance, in particular from my own Make Wi-Fi Fast project, stuff from Eero and many other companies. And my goal in this workshop is to try to get comparable open source, repeatable metrics based on different approaches being taken to the latency and jitter problems here. And I'll gladly work with anyone in order to get fair and open benchmarks of what the potentials we can achieve with the technologies that are being designed as well as being distributed today.
Thank you, Dave. Omer, you're next up. Omer?
I'll withdraw my question. Sorry. Go ahead.
Bob. We can't hear you.
Again, I was just trying. It's so long since I got into the queue. I can't remember what it's about. I've been talking on the chat. Sorry, pass over again.
That's fine. Gori?
Me?
Yes.
Oh, yeah. Yeah, so to Jim,
No, sorry, Gori. Sorry, I said Gori, but
oh, sorry.
Hi, I'm called Gori. Yeah. So I think I was talking to DSCPs and saying that I think they are very useful when you are dealing with your upstream and you are close to the marker, and many ISPs are actually passing these upstream and many aren't. And I think this is a thing that we should really start unpicking in the TSVWG working group. So I'll put my working group chair hat on and say, please come and talk there about this problem.
thanks, Gori. Björn, now it's your turn.
Oh, thank you. Yes, so to Jim, you said you can't subtract because the bottleneck link sort of moves around, and I agree when what you're measuring is the bottleneck link in that sense. But if you have the right metric, then the right metric will have that property that you can actually subtract. And that's sort of my point there.
I don't believe so.
Okay, let's discuss in a breakout room afterwards, right, then, because that's interesting. And then to Dave, yes, open sourcing that metric, the one I'm talking about, is something we're interested in pursuing. So let's discuss that as well.
Right. Now, Jim, your turn.
So everybody's saying the bottleneck link. There are two bottlenecks, one in each direction. Stop, and you can have a different in each direction at any given time, and it varies as the applications change. So stop saying the bottleneck link. It is bottleneck links, always. It's often the same, but it's very often not the same.
Thank you.
Bob, you are shaking your head no. The simple example is asymmetric in the home, and in which case the bottleneck is, with Wi-Fi, the bottleneck is often in different places between the uplink and the downlink. It's bottleneck links.
Can I just say why I was shaking my head?
Yeah.
Okay.
Yeah. Just the always. If you're not restricted on the ACK stream, there isn't a bottleneck in the other direction. It's not always, but I agree with you. It can be. Yeah.
It is commonly.
Yeah.
Torles, your turn.
Yeah, so just wanting to answer to Gori with respect to usefulness of DSCP, right? So there is no contract between me and any transit provider, right? So if I pass on the DSCP into the transit provider, what would they reasonably do? I think the only differentiation based on DSCP that makes sense through a transit path without additional contracting for differences of services would be to react differently to the new scavenger class we did recently in the IETF in TSVWG, but that's about it. Obviously, there is a lot more that could be done with your direct access service provider given appropriate contracting, but yeah, that's exactly where I think we don't even have standard DSCP meaning for, differences in elastic traffic.
Thank you. Bob, you're in line.
Yeah, this was I remember Gori reminded me why I just got in the queue. With Matt saying about excuse me, the DSCP, and we need to sort this out and stop it being bleached. But it's not just bleached because ISPs randomly bleach it. There's a reason why they bleach it, and we have to solve the reason why they bleach it, which is all to do with policing. And that's a really deep problem with the DivServ architecture. It's not just something go to them and say, look, stop bleaching this. But I don't think this workshop is wholly about that. And Matt was asking whether it was, but it's not. Let's not maybe go down that rat hole. But
thank you, Bob. Greg, your turn.
Thank you. I wanted to add to the discussion thread between Björn and Jim. it appears that we're talking about not bottleneck links, but bottleneck nodes or interfaces. And if that's the case, then we might look at different measurement. Measure not end to end, but measure on each hop that we traverse in both directions. And then it will give us advantage of instantaneous reflection of where the bottleneck or dynamic of these measurements will give us better clue and understanding. Because if we experience worsen metric end to end, when we try to troubleshoot and localize this issue, the picture will change, as Jim pointed out, and I agree. So it's dynamic. We need to have a tool and method and use the metric that gives us information already what we need, so we can do the localization. And that's probably seems to be a residence time, but we can talk that later. Thank you.
Thank you, Greg. Evgeny, you're the last one.
Thank you. So related to the question about the number of the bottleneck links or nodes, so in general case, I agree with you that there are several, there can be several bottlenecks. But today, the main part of traffic is generated in wireless networks. And if we consider the wireless networks, even maybe not Wi-Fi, but cellular networks, we will see that the bottleneck is there. Bottleneck in both terms, in throughput and latency, because cellular networks have very significant problems with delays, and if the users are cell age users, they experience very low capacity. So the bottleneck is there. Thank you. And after the break, we will have a lot of presentation related to wireless networks and to the issues in wireless networks. So I think they will clarify this statement. Thank you.
And that is the end of our session. Wes or Evgeny, do we go into the break now?
Yeah, so I think we have a break. Yeah, we definitely have a break according to our schedule. And let's have a break for 10 minutes, and then in 10 past whatever hour you have. So in 10 minutes we'll go back.
Thank you to Christoph for chairing the last 2 hours worth of discussions.
Thank you, Christoph. And after the break, Sam will chair the sessions.
And oh, look, my espresso cup is empty again.
Sam, do you have the slides?
Sorry, just replying to your message. Yes, I do.
Okay, great.
Do you want me to share them now?
It's up to you. Just
Might as well.
Yeah.
It's all right. We've got 8 minutes, right?
So, Evgeny, Sam, since you're both here, I think one of you should remind everyone that we should use the WebEx chat as a control plane and Slack as data plane, because once a discussion emerges in WebEx, it's very hard to note every cue, and people can get upset. So maybe
Sure.
maybe you can use the weight of the position to remind it.
Yeah, sure. And also, I will write it in the chat.
Yeah, it's just that very
nice-
easy to miscue.
The other nice thing about Slack is we have threaded discussions, so it helps keep the different topics separate. The WebEx chat is just a linear flow, and if people are talking about 2 or 3 things, it gets really jumbled.
And there's also a benefit that once this interesting discussion emerges in Slack, it is possible for us to include at least some of those ideas in the final report, if possible. This is absolutely not an option with WebEx chat.
The only problem with Slack seems it loves to sell me marketing, right? All the things it wants me to approve on. Maybe we should have just used the I don't know, some other standard Cisco IETF tool.
Slack is used by IETF, and it's quite standard in the industry. And yeah, everybody wants to make their living from somehow.
Well, I think the normal Jabber chat that we have in the IETF would be perfectly fine too.
So the IETF is actually possibly going to move to a different tool. I don't know if it was announced yet or not. We'll probably continue to use Jabber for working group sessions, but for a general chat too, I think we're heading to Zulip or something like that.
But would it be Slack, or is
no? It'll be most likely Zulip, I believe. I don't know if the decision's been fully made though.
As long as we are using Slack today, let's encourage everybody to make use of the threading. If you reply to a message, don't just reply in line, click on the reply in thread button, and that way we can have multiple discussions going on without them all getting shuffled together.
Yeah, thanks.
Very good point.
Thanks,
We'll get started in 1 minute.
Excuse me, would there be an opportunity to send the revised agenda in email rather than pasting it into a chat?
We can probably do that. Sorry about the interruptions today. It was due to last minute waiting for slides. Most of it's the same. It's just the last few presentations of the day are in a slightly different order. But other than that, it's the same. The website is still accurate except for the ones for today. And again, we still have the same problem that I talked about yesterday, where the person that can update the website is disconnected at the moment. So it's very hard to get her to update the website with the latest presentations and latest documents. But we will get that handled. We apologize for the delay. It's sort of out of our control.
Is there somewhere that we can find all of the submissions?
So all of the submissions, I think, are on the website, but again, not all of them are the final versions. We got very late submissions for a number of papers and a number of slides. We'll try and get the slides online as well, but it probably will be next week before we get that totally wrapped up, unfortunately.
I don't think it's quite as good as that. There's submissions that were a few days early that also aren't on there.
Yeah, as I said, juggling 40 plus submissions over mail was challenging at best.
Yeah, I think we can start. So this is the afternoon. Sessions will be chaired by Sam Crawford. So Sam, please.
Thanks very much. Okay, our first presentation is from Jerry, and it's titled "Observability is Needed to Improve Network Quality." Over to you.
Yes, thank you. I think you can move to the next slide. I only have one slide. This is a bit of a sort of big picture, top-down presentation, and maybe appropriately so because we're beginning the discussion on cross-layer, and there's more details and more specific proposals in the coming talks. And I also want to call out Colin Jennings, who may not be on the call right now, but was at least yesterday, who last year talked about this problem that if you're a content provider or user or network player, you don't often understand why some issue is a problem. You can't necessarily see what's happening on the user's Wi-Fi, or if you're the user, you don't know if the problem is at the network provider or at the cloud facility or the application. And that's a problem, of course, and it's a problem of limited ability to observe. Isolating a problem, debugging, and fixing it is difficult, and that's not desirable, of course. We want to have better service. And of course, this is not related just to problems. In general, people want to maybe measure things and understand how good certain network offerings, for instance, are or not. And not all aspects of desirable behavior are directly visible, at least not with the simplest measurements. Even with some more complicated measurements, it still leaves out many other things like various features and capabilities and security aspects of networks. And also dynamically changing situations is usually not shared to others. So we're basically missing out a little bit on things that we could be doing. And our paper with Mirja was basically proposing that the direction for solutions is more or better collaboration among multiple parties. So we're arguing that we don't just have like two parties, the sender and the receiver. We actually have many players collaborating to do something, and being able to talk to those other players would improve things at least somewhat, and in some situations. So we want observability. We'd like to be able to explicitly identify situations as opposed to inferring something based on some very indirect measurement. And if this sounds very abstract, it is. I do have some more concrete examples. The one that's not listed on the slide, but we talked about yesterday, is if you have measurements and you have data, please publish it. And it could be a continuous publication rather than one talk at a conference once during the lifetime of a system. You can also imagine that there'd be some sort of actual interfaces where, or ability to use a network for assisting in some measurements in some way by the user or by the application. Similarly, Robin is going to talk about capabilities for endpoints to produce information that could be assisting others in understanding what's going on. So that's another interesting angle. We sometimes have various kinds of probes and probing processes going on, which can be used. I'd like to see capability discovery discussed a little bit more. What does this network do instead, in addition to having this latency and this, bandwidth? What does it do? Does it do V6? Does it do, what kind of DNS and what kind of security and so on? Also, security would be really nice to understand what's actually going on. And sometimes you see like this immediate security situation that, well, my interface is connected this way and there's this security, but you don't know what's happening after that hop. And also when you use various kinds of servers, you don't necessarily know what's going on. You see that, well, I'm using the TLS thing, but what's at the other end of the server? So one of the things that we played with a little bit is using confidential computing to be able to provide some assurances of what happens to your information, let's say your DNS query histories and so forth, to try to limit the spread of information for various kinds of commercial and other uses. And of course, if you go for this observability, there's some constraints that we need to respect. Usually it's only possible for mutually beneficial cases and it needs to be explicitly decided and not sort of, randomly sending some headers and that other people look at. If you haven't read RFC 8558, and go read it, it's a good one. And of course, we do need standards. Again, Robin is going to talk about some of that. And finally, of course, you have to be very careful with data. We also talked about that yesterday. What do you give and to who? And obviously, you shouldn't give user-specific information necessarily, but I think we can handle that. So that's it, really. I think I'll leave the rest of the time for the others, or if you have any clarifying questions or other comments, please go ahead. I guess the other comments come later.
Thank you very much. Any clarifying questions from anyone?
Yeah. This circular buffer of some kind, right, where you keep stuff around until you're able to detect, right?
I'm sorry, was that a question for me? I'm not sure I understood the question. Circle buffer, what?
I think let's move on. If Nick, if I don't think we got the question, if you wouldn't mind following up in the discussion afterwards, that would be great. Okay, thank you very much for that. Moving on, we have Robin, who will be presenting merge those metrics towards holistic logging.
Yeah, thank you.
You're talking about this shunt paper, right? I think we've.
I think Nick Feemster still has his microphone on, which might not be intentional.
Yeah, that was this shunt paper. Yeah, I think we'd circulated that at some point.
Jenny, can you mute Nick, please?
Yeah. Okay. Let's go. So next slide, please.
That's the one. That's the one. Yeah. Exactly.
I'm sure the muting will happen sometime. Next slide, please. So we've been talking about all these different metrics that we might use to infer the quality. Next slide, please. Next slide, please. There we go. No, one back. Is this not the update? Is not the updated deck? Whatever. This is not the most recent deck, but it doesn't matter. The updated deck has just the left part of the image. So focus on that. So we've seen all these different metrics that you might use, and the observation that we made is that these are typically extracted from different parts, or at least in different formats. So for the lower layers, lower protocols, you typically do something in network or use something like packet captures, of course. But then for higher level TLS, HTTP, you typically extract these at the endpoints from inside libraries or platforms like, for example, browsers. And then you have this whole thing above the business logic, which is often something completely different, right? You have custom tracing pipelines or things like Google Analytics that people use. And this is, of course, logical to see. These things are implemented at different layers, kernel versus user space. And while we might want to use packet captures for everything, this becomes much more difficult once we start encrypting stuff from TLS onwards, right? Now, the thing is, these three different levels don't really matter. They're still useful for most use cases. But the moment you move to more complex situations, you really want a cross-layer visibility from at least, let me say, TCP all the way up top to the business logic there. And this is something we especially saw for things like web performance, web page loading performance, and video streaming, and I think that accounts for gaming, what we saw today, for example, as well. And the thing is that while we do have data from all these three different levels, let's say, it is still very difficult to get them all together and to analyze them all together in a single view.
Use it.
Yeah. And so that's one of the issues. And then we have, this is slide 2, with Quick, we have something that makes this both easier and more difficult, right? Because Quick is now encrypting everything. You certainly can't use your packet captures anymore to do anything, or mainly anything useful anymore. But the fact that Quick, most Quick stacks at least, are in user space now, or at least were engineered from scratch this time around, we can actually start logging things or grouping things more at the endpoints. So having both the transport level Quick stuff and everything that comes on top, HTTP3, but also some of the business logic, like we are doing this, for example, for ABR video streaming in our experiments. You can combine all of that into a single log, a single view, which is our QLog project, but you also have separate other projects using, for example, eBPF and things like that to extract things from, let's say, the TCP. And the idea is we might want to take this one step further, right? To go to the to-do on the slide to have the full cross-layer view, or at least maybe not to the full physical side. I don't know if that's possible, but as deep as we can go. And the idea there, this comes back to what I said to Praveen's thing before, because he touches on these things as well, is that I think it's not really doable to log all of this into a single framework, let's say a single API on the endpoints, but that we might want to extract these from the separate implementations or settings and then aggregate them in a post hoc fashion. So generate a single view from different data sources afterwards. This has quite a few challenges, as we said as well, because you need to somehow synchronize these and correlate them to the correct data is put together with the same stuff. And that is just for a single endpoint, right? And then the second part is that we also want this across multiple endpoints, client, server, but also all the edge servers and load balancers in between. And that makes it even more difficult. And most of our paper is about these challenges that are summarized here. Most of it is about that. And once we have that, this single view, then we can start creating tools to analyze and observe indeed these cross-layer effects and cross-endpoints effects much better. And like I said, I think this is going to be one of the main challenges going forward from there. Last slide, please. And once we have that, like single aggregated logs that have these full views, I think these could be very, very useful for then sharing with other parties as well. This, of course, again, introduces this privacy aspect that we've discussed multiple times this week. But like I said yesterday, we think this is fixable. We can do this via obfuscation or omission or aggregation for some cases. And we think this might enable or solve some of Quick's observability problems, for example, by sharing some of this sanitized data with, for example, network operators, who knows. But also crucially, I think that the bottom side there is the ability to share much more extensive data sets than we currently have, especially from industry to people like me, the pure researchers who would like to get this data. Now, I am not naive enough to think that privacy there is the main driver, that they currently don't do this.
Sorry, Robin, we're pretty much at time. If you could wrap it up.
I'm completely finishing. So I'm not naive enough to think that privacy is the only thing, and that just having a good way to handle privacy of these aggregated logs will solve that. But I would like to have a discussion if this can ever happen, and what kind of incentives would additionally be needed to incentivize BitCos to share more of this low-level data, so that we don't have to rely on their conference publications with very high-level conclusions. Thank you.
Okay, thank you very much, Robin. Any clarifying questions before we move on? Okay, thank you. Next up, we have Rajat, who will be presenting measuring and improving QoE on the Xfinity Wi-Fi network.
Yo, can you hear me okay, Sam?
Yes, I can.
All right, thanks. So, hey, my name is Rajat Gai. I'm responsible for network engineering and operations of Xfinity Wi-Fi network, which is a public hotspot network. Next slide, please. Next slide. There you go. Thanks. So set the context, Xfinity Wi-Fi network is a public hotspot network. We have around 21-ish plus million hotspots. For people who are familiar with cellular 3GPP architecture, it's built just like a cellular network. All the hotspot SSIDs are bridged back to our core network, which is a function you see there, a WAG, Wi-Fi Access Gateway, does all the subscriber management, DHCP for the clients that connect, and all the clients can now connect over an Ethernet over GRE tunnel to our WAG. Typically, a customer of ours would be 100 miles from the WAG. So that's your dot one. We have around 20 plus hardware types in a network at any given time. Every Wi-Fi socket that out there is out there in a network, typically in 3 flavors. There is residential, there is outdoor, which is on the strand, and then business locations. At any given time, there are 200 and plus even firmware locations floating around in a network. On the bottom there you see, we basically wanted to use, we do both active observation and passive observation for quality of experience. Active observation, actually, we do walk tests with synthetic clients, but they're limited by time and space and number of samples. But passive observation is here what we are here to talk about. We do passive observation of KPIs, where it's shown on the top. It's basically at our core network. And then our goal is to use passive observation as a proxy for, especially latency, as a proxy for quality of experience on our public Wi-Fi network. Next slide, please. So we use TCP connect latency as a primary predictor. It's basically measuring SAC to ACK from the network to the client and back. From empirical testing, we have seen it's a pretty good proxy for RTT. Just given the scale of our network and number of TCP connections, you'll see in a minute, measuring RTT on a per transaction basis were like very cost prohibitive and doesn't even scale. So, and there is enough richness and diversity due to complex web applications. There's enough TCP connections per application when a user connects to a network that we actually found this is a pretty good correlator to RTT. Then we also use TCP retransmissions, basically, which is percentage of frames that were retransmitted in the entirety of the session. Again, we do statistical distribution, but you have to have a benchmark. TCP connect latency benchmark is 150 millisecond round trip from the core network to client and back, which includes the uplink and downlink of the Wi-Fi to the client. And then 4% is our marker. But again, we are interested in P98, 99. So, but we do need a benchmark, so which is 4% for us. And then finally, throughput. Throughput is not for us. It's not a KPI. It's an outcome. So if you keep improving a network by doing network optimizations and reducing latency, retransmissions, we actually see that the actual throughput consumed by users for applications like video, which is the primary application in a network, actually throughput goes up in those markets where we reduce latency. Next slide, please. So this is typically an example. Like what we do is we do KPI instrumentation, at the point of observation. 24 hours. These instruments out there, they just measure KPIs. for billions of sessions. You see here, again, each one of that represents an individual TCP connection attempt. So, and then they aggregate at night, and then next day it's ready for passive observation and data collected. So this basically, what you see here, this graph is actually a statistical distribution, CDF and PDF for all the connections like that happened before. Again, this is basically capturing every, and then we basically then bin it into different cohorts. You see a subscriber type cohort, AP class, AP firmware, AP hardware, different markets. And then we use that for our not trending that our network is measuring up to the benchmarks we have. But then we also, all the proof of concepts we do and optimizations we do at a national level, we can actually compare before and after, which we'll talk about later a little bit, and then see we are actually making improvement. Again, as you can see, are close to like 98% of our TCP connects are below 150 millisecond benchmark today. But again, we want to keep moving those samples to the left as much as we can. Next slide, please. Same thing with TCP retransmissions. We do the statistical sampling. We have a lot of interesting observation on what these individual TCP connection types are, how long they are, how many packets, but that's this for a separate day. Again, like you see, like 80% of the samples are within 0 to 1% of TCP retransmissions. But on the extreme right, you see like there's 2% or above 25% TCP retransmission. Those are the ones we are after. Why that happens? And the biggest thing for us is challenges of cell edge. So one takeaway I would take from there is, if you have one of those experiences where you're standing on a stoplight and your Google Map stops working because you're randomly connected to some Wi-Fi access point and negative 90, negative 88, negative 80 RSSI. People who are representing smartphones here, please go back home and tell your engineering to do a better connection manager. If you have 4 bars of LTE and 1 bar of Wi-Fi or less than that, please connect that and better application design. Next slide.
Yep, we're just at time here, Rajat.
Perfect. You can see this. This is a standard A/B test. That's how we do network measurements and improvements. Nothing new here. We compare markets, and then whatever works, we make that optimization change, and this is then wash, rinse, repeat. That's pretty much it. Thanks.
Okay, thank you very much. Before we move to the discussion, are there any clarifying questions on Rajat's presentation? Okay, all right, well, we'll move to the discussion. Again, just a reminder, please put +Q into the chat. And I think our first comment or question is from Tordas.
I wanted to ask the obvious question about Yari's presentation, which, first time when I was trying to introduce visibility into the IETF 7 years ago or so, I was hit with a lot of backslash on privacy. I don't think that has improved anyhow. If anything, it's gotten worse depending on which company you're working for. But to give a simple example that I think would be interesting today, not even about DSCP, but I've seen a lot of home routers that have improved, the low latency by identifying and putting into a low latency queue TCP acknowledgement packet. So now we're going into QUIC and a bunch of other protocols. So we don't have that information in the network anymore. And it's not even just the troubleshooting, but it's the whole, AQM and queuing and low latency that will be suffering. So I'd really love to hear from Ari some, more explicit ideas about, what exactly are the bounds of visibility that we can do to basically comply with whatever the IETF feels is, the necessary privacy.
Thank you. Brandon?
Yeah, I think there's been some discussion about what data could be shared from between companies that have access to it and other people that want to do research on internet quality. And I think a question is, when would that data be actionable? Because it can be a lot of work to export that data, and so what would you do with it? To give an example, if I'm looking at internally a session where somebody was playing a video and it stalls, I'm going to want to look at what was occurring at the CDN, what was occurring for that connection, how are we using network resources, so that we have multiple HTTP requests in flight that we're competing with each other, what was occurring for other users at the aggregate, is this user connected to a cellular RAN that's congested, or did they just walk into a subway station and lose signal, and that's why this video stalled? And then you really have to extrapolate from all that. You can't just look at one session, you have to find out how prevalent is this type of problem, and then experiment with possible solutions. And the experiments are often making changes at the business logic, as Robin talked about, but also at the transport or deeper layers. And I think that kind of becomes a barrier to making the data, to exposing the data, because it's not clear what other parties would do with it or whether it would really be actionable for them. And so I'm curious to hear from others as to what they would do with that type of information.
Okay, thank you. Dave?
Going back to the previous presenter's slides regarding the SYN-ACK pair, I think that's a very worthwhile optimization if done carefully. I had a random piece of data that I would love for more people to try to confirm, or perhaps to be confirmed by that presenter. I actually saw SYN packets being remarked to AF21 and surviving transit to one of my test servers over a given cable modem over a given provider. And I'm curious if that's an actual random data point or a real one or not.
All right, thank you very much. Bob, you're next.
Yeah, this is in response to Yari's and Robin's talks. I think in some cases the perfect, again, might be the enemy of the good, where we want, global access to data, and in the process we don't get anything. And maybe, we ought to be looking, or the IETF particularly ought to be checking that specs and stuff at least have like management interfaces to do monitoring and stuff like that, which I pointed out not long ago that none of the experimental AQM RFCs have anything to do with monitoring in them.
Oh, the scales are different, at least on the COVID one, right? I mean, during COVID, the scale looks very different.
Is this breaking in
so,
again?
I mean, is that what we're supposed to take away?
Wes, are you able to mute Nick?
I muted him again.
Okay.
Thank you very much.
Right. Yeah. So on those RFCs don't have anything to do with monitoring in them or management, and so even if an ISP wanted to measure whether it was to blame for something, let alone someone outside trying to measure that, they can't do it. So the IETF needs to be a bit more have more diligence about checking management stuff. I know a lot of people find it a pain, but it's got to be there.
Okay, thank you, Bob. Yari?
Yeah, Bob has a point about the perfect being the enemy of good. We should not shoot for sharing everything, obviously. And back to Torres's point, obviously it's again difficult to share everything, and you can't actually have like a one-size-fits-all answer. Unfortunately, you have to look at all the specific cases. Like, is it okay to share this or not? I mean, spin bits and ECN bits and so on is people are relatively comfortable with that. If you start sharing, I don't know, application identifiers and the like, then people get more uncomfortable. But just to give you some examples of the kinds of things that you could actually share, I mean, and certainly I think everybody should be okay with providing information about what the security of the system is that you're connecting to or through. You should be able to do capability discovery for sure. With regards to like networks providing measurement data, if you request for a specific measurement or something that relates to your own flow, that seems a reasonable request. What do you see out of my flow, or what do you see to this IP address? If it's like a content provider, they could certainly provide some aggregate results that, well, in your area or in your country, the average delays to our services seem to be like this, and in your ISP like that. I think those kinds of things are reasonable, but there are obviously a lot of per user, per application related data that is not reasonable, and we just have to look at it case by case.
Thank you, Michael.
Okay, just a quick answer to Dave Tart when he was saying that he saw this data point with one AF42 packet. So yes, it happens. Yes, it exists. We've measured that in the past, and Gore's group has done some measurements as well. So I mean, DSCPs sometimes pass through the network unharmed. It's rare, but it does happen, and there are numbers and statistics. So I mean, it's not true that they're always breached. That's maybe a misconception, but very often, yes.
Okay, thanks very much. Wes?
So I'm going to put on my pessimistic hat here for a second. You know, we discussed a lot yesterday about the economics of being able to, you know, instantiate these metrics that we may want to come up with. And how do we do that where we can actually, convince the major players that they want to deploy something that allows that end-to-end debugging where the CDN actually can reach all the way into the user side of things and see what's going on. In the past, there has been network operators that have tried to promote, fine-grained access control where the smaller ISP can query the upstream against that interface, for example, over SNMP or something else under network management. But that's really only single hop only. And I'm curious, how do we incentivize, turning on some sort of debugging metric when nobody wants to have the finger pointed at them as to be the cause of the problem, right?
Thank you, Wes. Torlas?
Just to answer to Jari, I think I'd perceive that answer to be a fair assessment for the internet, where I think the privacy expectations and the limits there for visibility are quite different from private networks, and I think it would be very helpful to also provide more background on the experiences people have had and requirements that they do have in private networks, even in things like enterprises, right? I mean, when Microsoft was implementing INSERV support into Windows XP, it had a very great, policy mapping from knowledge about the application exercised by the system operator over to, for example, DSCP or RSVP, right? And likewise, if you look at industrial networks, then you exactly have examination all the way up into the application layer by intermediate devices to basically foster the performance and other metrics, right? So I think we should be aware that the IETF isn't only for the internet.
Okay, thank you very much. Dave again?
Having recently run deeply afoul of the privacy issues in my own work, I would really love to have guidance as to, in particular, being able to widely expose congestion information from a very specific structure called the TCP_info structure. I just pasted it into the /chat, and someone coming up with a good set of rules and guidelines for being able to widely collect and or distribute that information would be a great help to me presently.
Okay, thank you. The queue is getting low. If anyone has any questions, feel free to add them to add yourself to the WebEx chat. Jim is next.
The enemy of the good is the perfect. I will note that with most of the problems being in the very edge of the network, whether it's in a home environment or a corporate environment, a lot of the privacy issues don't exist. They exist primarily when you cross administrative boundaries. And so don't believe that just because it may be really tough, if you will, inside the internet, that working at this problem isn't worthwhile, because it is. We need to be able to diagnose the networks where the problems occur.
Thank you, Jim. Okay, Wes, you're up.
Dave, we just need a dialog box on every single home router that releases that TCP info. I mean, that's the answer to privacy, right? Is that you've got to get authorization to release, and that is very hard. We have so many instances of that happening now, with every phone saying, hey, do you mind if I use background CPU in order to do federated learning for data? And maybe federated learning techniques are sort of one way that we could look at how do we measure a network of 10,000 people in a way that doesn't release their results, if we can do it in some mechanism that does the aggregation sort of on the host like we do with machine learning.
Thank you. Bob? Bob, you may be on mute.
Having the ability to monitor things on a device isn't just for the ISP. Obviously, if it's your home device, you can do it yourself, and then you can determine whether it's your device or something else that's causing the problem. But if you don't have it there in the first place, the ISP can't use it, the user can't use it, no one can use it. It's got to be there.
Yep.
Okay, Roberto?
A lot of us are likely to know this, but we can apply it to this as well. There's having data, and then there's being able to interpret data. What I mean by that is encryption is your friend. So if we're rigorous about encrypting things and we come up with reasonable key management things, as has been discussed, by the way, in the chat here, it helps us solve at least the security and or privacy related problems with it. And then we can orthogonalize the when to collect, when to trigger, and where to store things separately.
Thank you, Roberto. Jim?
I will note that if you will, end user customers have incentive to release information to their ISP when they're having trouble. So I think that this is something which can get worked out. Similarly, between peering, the different carriers may, the different networks may wish to work those things out, but we have to make sure we can easily get the information and make it actionable.
Thank you very much. Dave?
All right, so let me point to another place where privacy and stuff is both misinterpreted by the public and also very difficult to do research on. A lot of my work has been focused of late more and more on video conferencing, and we don't get adequate statistics back from the host of these things, and yet the pass that the server has is unencrypted. These servers have access to the unencrypted data, and that's really worrisome to me. The perception in the public, however, is that it's encrypted, it's all safe, and that really isn't the case. So Julius Krobacek last year wrote a thing called Galen in anger, mostly for teaching, and I have been working with his group to do adapting vast congestion controls and being able to look at the statistics with my users' consent to try to build a better video conferencing platform. And again, the possibility of aggregating those statistics correctly, figuring out what statistics to collect, is a really large problem still in the video conferencing world.
Thanks for that. Jari?
Yeah, 2 comments. People are bringing up the sort of limited network or, my network type situations, and that's a valid point, of course. Just not, at least personally, a huge believer in this separate networks. In the end, they tend to be actually multiple administrative domains. Like, even in my home network, there's some applications on my phone and the app and the corresponding server actually believe that they somehow own this thing, and maybe rightly so, maybe not, but it's actually multiple entities, so it's difficult to coordinate everything. And the other point is that, going back to this perfect versus good, I think the answer is not, this huge architecture, even though I was basically talking about it for sharing everything. It's really small steps. Maybe it's like a small improvement in, traceroute or, the use of some probes or periodic publication of content provider delays to different ISPs or regions, aggregated and, anonymized, probably, of course. So I think that's the answer we should be looking for, not the grand change.
Thank you very much. Matt?
Yeah, so I want to tell two slightly related stories about TCP info. The Measurement Lab project collects TCP info on fine-grained snapshots. I sort of talked about this yesterday, and all of that data is public. The telemetry from the connection telemetry is naturally available to the content owner, the content provider. And that is the source of the information in an encrypted internet. Something that people might not know, and I actually don't know how much of this is public, so I have to be careful if you attend things like NANOG. Google shares with directly connected ISPs subnet-grained statistics on things like packet loss. And this is our way of helping the ISPs be as good as possible with what they do. And the generalization of this applies to any large content provider, applies to any CDN. It's the people who are serving the data who know what's going on in the network. And if that data is binned by the details of retransmissions and loss and delay and whatever other metrics you want to do, there's no reason not to share it with the customer's ISP. It does not reveal anything about content, or you can control how much it reveals, and it's very powerful.
Thanks very much, Matt. Brandon?
I think following up on Matt's point there are other content providers that also share with ISPs this type of information, but the key challenge is always finding out what signals should be shared. In that you can, more is not always better. Talk about packet loss. When we changed from cubic to BBR, packet loss rates in some cases increased for some networks. And that's again because BBR is going to be more aggressive under some circumstances when cubic would have backed off. So a network operator would see an increase in packet loss rate for their network, despite the fact that performance perceived by their end users, quality of experience, actually improved. And that doesn't make sense to most people, but that's because packet loss is a function often of the workload, right? And that's why it's also sometimes difficult to use data sets like those from MLab, because they have a very specific workload. They're trying to profile the connection. And so whatever you see in that TCP information is not necessarily representative for a different workload. And that's what you have to keep in mind whenever you look at any of this type of data.
Do you want to follow up at all on that, Matt?
Yeah, I just put myself in the queue.
Perfect.
So what we're trying to do at Measurement Lab is to derive metrics. So for instance, the responsiveness metric comes from a bulk transport test. It's a side signal off of a bulk transport test. And at some level, it predicts, it tells you something about what the queue management strategy is for the connection, which may or may not. The trouble is you got to put in a lot of caveats. You're right. It's a specific workload. On the other hand, it does set a bound for what the network is likely to do for other workloads. And the case that I was humming and hawing about is that one of the things that we can't see is whether or not there's separate queues for different flows and flow isolation. But we can measure statistics about the flow that our connection is using. And that information is useful and is valuable, but not if QoS is being used, for instance.
Thank you, Matt. Anna?
Yes, I wanted to follow up on what Brandon said, because I think that's a very important point. And in general, if we talk about sharing of data sets, it's also very important to have the appropriate metadata for those key metrics that are captured so that you can actually derive correct conclusions, because otherwise clearly you can also make very incorrect conclusions if you just have a limited set of data available. So I think the metadata is very important if we talk about sharing data sets.
Okay, thank you very much. And Wes, I think you have a question.
We have some more. I'm going to agree 1000% with Anna. You know, if you don't have labeled data, it doesn't really matter if you have some metric that you have no idea whether that translates to the quality of experience at the user side of things, right? If you could have all the loss in the world, but if they had a great video conference anyway, as somebody just pointed out, I think Brendan, it doesn't matter, right? So if you don't know that the metric corresponds with user experience, then we're sort of lost.
Thank you. Gori?
Yeah, I actually was on a similar thing to Anna. I was just slower in responding. The metadata is so important to know what was going on at the same time when you have the data, because when you look at it later, it could be utterly meaningless if you don't know what the user experience is, if you don't know what the other traffic was that was happening at the same time. It's all needs to be seen together to get a proper response, and that's kind of tricky. It's something that we don't really know quite how to do, I think.
Okay, thank you very much. The queue is at 0, so I'll offer one last round of opportunities to get into the queue if anyone wants to.
Sorry, what do I do to get in the queue? Plus Q or something?
Well, you can just start asking a question if you want.
No, it was
yes,
more.
You would do, yeah.
So one of the things we have observed is that part of this conversation is network selection. Most mobile devices have more than one radio access technology to connect to, and we have seen like some of the improvements can be made in correct network selection for the right latency. I've seen, we have observed that connection managers and especially smartphone devices have pretty strong affinity to the poorest of poor Wi-Fi signal when there may be a much better cellular signal available. So, some more focus on this area. Again, we are doing network admission control on our side to put admission control. Like if you can't sustain a connection quality below our KPI, we would start not admitting those at the time of association. But I believe app developers and connection managers can do a much better job as well, because Wi-Fi, unlike cellular, is a more federated link management system connection as opposed to cellular.
Okay, thank you very much, Rajat. Are there any more entries to the queue? If not, we can take a short 3-minute break before the next batch. Okay, Roberto, you snuck in just in time.
I'm seeing a discussion here about packet loss, and I suspect we all know this, but I'm just going to say it anyway, just to make sure we're all on the same page. Applications don't give a flying what to who's it about packet loss beyond, I might increase my buffer bloat a little bit. Applications will happily, like Zoom and other things, they'll happily like send packets, and if they're dropped, okay, I'll send more packets, right? And we have congestion control because that's obviously a bad strategy overall. But I'm just wanting to make it clear, like we're talking like the applications care, and the applications don't care for any first order impacts. They're impacted by the second order impacts. They may care about that, but in general, we don't see application writers really concerned with that scarily enough. So yeah, like I said, we're probably all on the same page. Just wanted to say it.
I think that might change a little with Quick, but we'll come back to that. Brandon, do you want to go next?
I think, again, just on the packet loss point, looking at packet loss in isolation often isn't going to be meaningful. If I have a 1 millisecond propagation delay between me and the server, I can recover from loss very quickly for content that's fetched, right? If I have 100 millisecond loss, that means any packet that's lost, unless I have something like FEC or I'm doing aggressive retransmissions, it's going to take 100 milliseconds to recover from. And if I have 100 millisecond boundary, like on this call, if I want this real-time audio to have less than 100 millisecond jitter buffer, I've already exceeded that with that propagation delay. So loss in isolation as a metric is often not useful for understanding QoE.
Okay, thank you very much. We're going to close the queue now. We've got 2 more. We've got Dave next.
All right. I agreed almost to everything what was just said, except that there's no retransmission in video conferencing. Typically, you just blast another frame, so there's no induced latency at all for having dropped the packet, aside from typically video distortion field.
There's keyframe retransmission, but yeah.
Taurus?
I mean, I once had on a global path from the US to Europe in a corporate network, 0.5% packet loss because of a bad transceiver. And guess what? Everything was so slow that I didn't see a difference in TCP, but then I was doing video conferencing and it totally sucked. There was not FEC in these video conferences. And then it was ECMP, so I couldn't even reproduce it on other system. Guess what? It took me more than a year to figure that out. So really the diagnostic and the ability to also do that segment by segment or so, and not only end to end, are really crucial.
I think we've got time for just one more from Cullen.
I'm just going to comment on largely how Zoom, WebEx, and WebRTC largely work. I mean, it's true that on most of those leading deployments, there's an incredible amount of FEC used. During the height of the COVID crisis, where there was having a lot of congestion, and sort of before like YouTube and Netflix had ramped their bandwidth down, we were using more bits for audio at one point than we were for video for the full redundancy audit. Okay, like there were several, like, you know, a small, 10 kilobits per second audio codec stream had been expanded with FEC into over a megabit. So it was pretty extreme. So there's a lot of FEC, but there is also a lot of retransmission used on those things too, because it's very hard to recover from everything with just gross amounts of FEC. So all of them will use retransmissions in some case, or a NAC type scheme, some variation of I lost your iframe, give it to me again. And that really ups the latency. And if you look at the latency of all the leading conferencing products over the years, just running on a network with basically, not accounting for network latency, the amount of latency the application is adding in is going up and up over time. And nowadays it's gotten to the almost ridiculous period. Like I see on the the educational versions of these products often provide worse environment than the enterprise version of it because people are trying to keep the cost down. And the education ones often have latency that's just, I can't actually see how anyone really uses them for a really interactive call. So sorry that's such a long answer, but I wanted to throw in a few tidbits on that.
All right, thank you. Moving on to our next series of presentations. The first one is from Cohen on challenges and opportunities of hardware support for low queuing latency without packet loss.
Yep, thanks. So I'll talk mainly about cross-layer issues that we found putting low latency AQMs in Wi-Fi CPEs and the importance of detailed measurements. We see that these issues result from past mindsets, or call it the former design goal, that higher throughput equals or was better regardless of latency. And maybe also a second order expectation that low latency traffic doesn't need high throughput. So maybe before continuing, I want to make clear that all of this doesn't mean that we can't improve latencies under congestion today using the existing lower layer protocols and chipsets. Most of the time we can easily gain a factor of 10 to 100 today by identifying and removing these built-in rate optimizations. So maybe next slide. When we speak about low latency, most of us think in terms of priority and guaranteeing bitrate, like in DiffServ. But most existing applications today actually need both low latency and high bandwidth, which is more difficult to achieve continuously, and especially guaranteeing that this bandwidth is available all the time, especially on mobile networks. So it would help that the network can give a feedback to applications on what rate to use. And L4S is actually basically a way to control the rate of flows, even without having a queue at all. You can see it as an extra tool that is missing today once this rate is under control by that mechanism. Schedulers that give priority will only reduce latency. So they don't change that rate because it's already under control by that feedback. So in this way, you can have a kind of net neutral fair share policy so that you can give all the throughput, all the flows the same rate, but still have some who needs low latency, a zero or very small queue. But also other policies can be used for managed services to keep latency low under all network conditions instead of purely guaranteeing a high throughput. But the result is that not only the network is responsible for low latency, but it becomes a cooperation between networks and applications. That's important. Next slide. So all this requires a different mindset when you think about this, and people really working on trying to reduce latency in endpoints probably often face the effect that bigger buffers get more throughput. So the bigger buffer you create in the network, you need to create a big buffer in the network to get actually higher throughput. And it is usually unintentionally, but is a pure result of this over-optimizing the rate. And the problem is that if you try to get a smaller buffer, you get lower throughput. And this should be removed from network designs and lower layer protocols, because not only the implementation, even the protocols work against you, as this is, of course, completely useless and works against trying to get low latency. Next slide. Maybe a few quick examples. I'm not going to go too much detail, but look at the first box. I see the layout is a bit messed up, but it's still visible. So you see in a scheduled medium, and there is a lot of packet aggregation. Everybody is sending for a long time. If you unilaterally try to reduce your sending time, you only reduce your throughput, you hardly reduce the latency. So these low layer protocols really need to look at giving enough scheduling opportunity for all flows. Also, if we see in the lower box, you see often that, and it's also mentioned by some people already on this call, that hardware accelerated and physical layers queue up a lot of packets that are sometimes even invisible to manage. So also there, it's important that things are working together. Next slide. So in the top there also the impact of bursty technologies in one part of the network, or even network interfaces or stacks of an end system, will cause potentially drop or in future further lower rate links. And I believe there are proposals already for adding playout timestamps on individual packets, which will definitely help, and I can support that. Also, access to headers for ECN is important, and we need to be able to set ECN in an as late as possible stage. And if not accessible, we should consider implementing ECN in lower lanes even. In the next slide.
Okay, we're pretty much out of time now.
Yeah, coming back to the measurements. Here we see a cumulative plot of latency that every packet experiences in different stages, and it immediately shows where things can be optimized. If you look at the gray curve, but quickly also, if you really have the CDFs of the different stages in the network, you can see also in here the black curve is the MAC aggregation time, the load, which is pretty good in this case. But even then, this chipset needed an extra stage, and we have to double the latency. And especially if the MAC conditions are worse, it's always doubling everything together. And maybe the last slide quickly. I noticed a lot of ideas about tools to measure network latency, but Also, tools to measure application cost, latency, or induced latency must be considered, I think. Probably not many people would like to hear this, but it's also useful for users to know which applications cause most latency or problems in their networks. But the security aspect also has been discussed already, of course. That's it. Thanks.
Okay, thank you very much. Any clarifying questions before we move on? Okay, then over to you, Ken, for state of Wi-Fi reporting.
Oh, okay. Thought there was somebody else first, but I'll take this. Next slide, please. Sorry, I didn't know animations were active on this. Can you fill up?
Do you want me to just click through?
Yeah, thank you. So I see it. We have software that collects data to perform diagnostics and optimization of both broadband lines and Wi-Fi. So one thing we do is we put an agent to the Wi-Fi CPE, the gateway AP. And then that collects data, sends it up to the cloud, and if you could see the other part that's supposed to be there, it goes through an anonymization process, and that little graph over on the right there is a histogram. So we collect data from millions of lines at multiple operators' locations. I mean, to start, the data has no user information about it whatsoever, and then it's all aggregated together into a histogram, so there's no privacy concerns because it's only aggregated across all of North America and all of Europe, where we have deployments, you know. So we pull in a lot of data. And we did an analysis for the DSA, the Dynamic Spectrum Alliance, who does a lot of interesting work on, you know, changing around rules for access to spectra for Wi-Fi and for cellular. And we found some salient parameters of interest, particularly to look at trends in data over time. So there's your typical things, the traffic, you know, the throughput, speed, latency. There's also kind of Wi-Fi specific things. Congestion is basically the amount of contention due to stations on your own access point. Interference is from stations connected to neighboring access points that also use up some of the airtime. And we also collected a number of broadband statistics. We get a lot of broadband data, but we only included some of it in the study. So next slide, please. And help me with the animations. So one thing we did with this data, not too far.
Sorry.
We plotted trends. So like on the left, you can see the total amount of Wi-Fi traffic in Europe. We also have plots for North America. And you can see for both 5 and 2.4 gigahertz, the trends are increasing. The 5 gigahertz spectrum can carry some more speeds. So there's more traffic there. And when we look at that, the Wi-Fi traffic doubles approximately every 3 years. And you'd expect, you know, a similar increase in interference, congestion, et cetera, without any more additional spectrum. And another analysis we did that was quite interesting is when is Wi-Fi limiting the speed? And so that's what the plot on the right is showing. 2.4 gigahertz Wi-Fi is often slower than the broadband speed. These are downstream speeds. 5 gigahertz, well, you might look at it and say, well, it went up to, you know, only 20% of lines are limited by Wi-Fi, but A, that's a lot of trouble cost, 20% of all your lines, and B, it's going up. it's going to be a real problem at some point in time, especially with, you know, fiber and all, increasing the speeds of broadband. Next slide, please.
Okay, we're almost at time.
Yeah, so we looked at individual parameters, you know, here and plotting the trends by linear regression again. And this is real world data, so you see some kind of oddities, but we take the overall trends on the right and we basically just take a simple linear sum of traffic, interference, latency, and subtract efficiency, because as efficiency worsens, you know, things get worse the other way around from the others. And then you can see in this table, depending on the region, the band, the overall Wi-Fi spectrum need increases about 25% annually. And that's equal to really a doubling every 3 years. When you know, do that compounding of 25% annually, kind of the result is we need more spectrum. And, you know, the 6 gigahertz spectrum is helping. We're hoping to get the full 6 gigahertz spectrum usable by unlicensed, including the upper 6 gigahertz globally. We're going to need at least that much to keep, you know, users happy. And I'll note there's a link to a full report, which is a 48-page paper with quite a number of plots and interesting results in it. And we're continuing this study, and we're looking at more parameters. We're stratifying according to, you know, the channel bandwidth, according to urban versus rural, and some other studies. So thank you. That's all.
Okay, thank you very much, Ken. Any clarifying questions before we move on?
I just wanted to say thanks for the most exhaustive Wi-Fi statistics I've seen yet. Thank you very much.
We do have data, yes.
Thank you, Dave. And Ken, I think there is a clarifying question for you in WebEx, asking for a URL to be pasted to Slack. Okay, on to our next presentation from Mikhail, talking about cross-layer cooperation for better network service.
Well, good morning, afternoon, evening for everyone. My name is Mikhail, and today I'd like to emphasize some of the problems we face when we try to measure the the quality of experience for the end users, and advocate for the cross-layer cooperation as a mean to solve them. Well, next slide, please. Well, yeah, okay. If we are at the application and we would like to measure some some network performance, we can face several challenges. First of all, today most of the user data transmissions include at least one wireless link. I think it's rather obvious. And the problem with the wireless links is that they have really different properties compared to the wired ones. Like you have different rates for different users, different packet error rates, etc. And moreover, at the wireless links, except for the queuing delays, you get a lot of protocol-induced delays. For example, if you try to measure the end-to-end latency by some ping measurements, which I call the single packet measurements at the slide, then you often face the delays, the protocol delays. Like in LTE, you can face the retransmission delays. In Wi-Fi, you face the same delay also. And the problem is here that first, they are really frequent, and second, they actually present at any load. so they obscure the actual load and the actual network state for the measurements, because because they present at any load. Then if you try to measure, for example, throughput, which means you want to send multiple packets to the network, or you would like to measure the network capacity, which means you would like to, for example, send a couple of packets and measure the delay between them at the receiver side. Well, you face the problem that the wireless networks have very high degree of aggregation, so they create a very bursty traffic. Well, they do this just to optimize the throughput, because the more aggregated are your transmissions, the less overhead you have for control data, for channel access, and etc. So all of this means that, as on the slide, that single transmissions on modern wireless include dozens of kilobytes of data at once. And all this data arrives at the receiver simultaneously, which means that you do not actually have anything to measure between the packets. At the receiver, you feel like all packets have arrived to you simultaneously. Moreover, if you have retransmissions, and you very probably have some retransmissions, because when you transmit a dozen of packets, the probability with a single packet probability of approximately 10% as a standard threshold, then for a dozen of packets, the probability becomes really high. And well, all the modern L2, let us say L2 layers or L2 protocols at wireless, they try to provide like linear arrival of packets, or in order delivery of packets. So all the packets waiting in the queue will, all the packets after the lost packet will be waiting for you, will be waiting for the retransmission, and then arrive simultaneously aggregated even higher. Next slide, please. And so
we're almost at time, by the way, Mikhail.
Yeah, just a couple of seconds, please. So main point of this slide is that well, we if we had a kind of cross-layer cooperation, if we have a communication between applications and the network devices, we could exchange this information. We could efficiently learn the requirements of the applications. We could efficiently know the state of the applications, and the well, that can be done privately, because nowadays we anyway have DPIs. We anyway have well, some approaches to analyze traffic, but in the better case, the applications could just reveal this data to the network, but not the private data, but the metadata or the properties of the flow. And on the other side, the network devices just could advise the applications what to choose and what rate to choose, and say what are their conditions. So that's basically it. Thank you for your attention.
Thank you very much. Any clarifying questions before we move on? Okay, thank you. Moving on to packet delivery time as a tiebreaker for Wi-Fi access points. I don't know if Francois or Olivier is presenting.
Yes, it's Francois. Can you hear me?
Yes, we can.
Okay, great. So hello everyone. So my talk is coming from some problem that we encountered when we were doing some experiments using some Wi-Fi access points in our lab. And so, as you know, there are a lot of use cases and a lot of devices using Wi-Fi, from file transfer to cloud gaming. Next slide, please. And so These different use cases have different requirements, so throughput is important, but we also said several times today that the latency is also important for some use cases. For example, for online gaming or cloud gaming, you will need a low latency, and maybe I inverted online gaming and cloud gaming on the picture, but basically these use cases will need quite a low latency. And next slide, please. And sometimes when you use the Wi-Fi, you have access to several access points, and the users basically never decides which access points they use, if they have access to several ones. Often it's the device that chooses the last one that they used or something like that. Next slide, please. And so if something goes wrong when they're using their device to do some real-time use cases, how can they choose the correct access points? If you look at the metrics that you have currently, it's often only showing the bit rate and some security information, but nothing about the latency or the jitter. Next slide, please. But with the same bit rate and the same configuration, the same distance, you can still have different latency or different jitters. Here it's an experiment we had from our lab that made us apply for the workshop, basically, is that we have the same configuration, but we change the channel, and basically one of the channels is more crowded than the other, and this implies retransmission, retries at the MAC layer, and so sometimes a larger latency. Next slide, please. And so basically it's not revolutionary, but our proposition was just to maybe announce some latency distribution information to either the user or the application. For example, for the user, currently they see that. Next slide, please. We could have some information, some visual information for the user to tell them that the access point they have may be suitable for some real-time use cases. And we can do that on the Wi-Fi driver when we upload data, monitoring the delivery time of each frame, for example. And so that's for the user. Next slide, please. And for the application, for example, in cloud gaming, you download some video, but you also upload some inputs. If you have some information about the distribution of the jitter on some access points, you could do something at the application level too, other than asking to change the Wi-Fi access points, if there is any. You can, for example, for games that are not too latency sensitive, you can use a playback buffer that is not too large. For example, strategy games and stuff, it could still work if you don't need too much reflexes. And if the user wants to play really latency sensitive games, you know at the beginning that there is some jitter with this channel, and so you can discourage the use of these access points. Next slide, please. And so there are other use cases for exposing this information to the application or the user. The device could also do multipath. If you know that the Wi-Fi has a large jitter, you might prefer using 4G, for example, and stuff like that. But we discuss more use cases in the small article we sent to the workshop. And so that's it for me. So thank you for your attention, and don't hesitate to ask your question. Thanks.
Okay, thank you. Any clarifying questions on this topic? I actually do have one super brief clarifying question myself. I saw on one of the earlier slides there was a small icon next to the Wi-Fi SSIDs that were listed, but I think the image has come out quite blurry. What was that icon intended to convey?
Yep, so it's on the 8th slide on the PDF. So it was just for an illustration. Here I added a gamepad, for example, for Google. They have their Stadia application, so they could add some gamepads on the icon to say that you can play Stadia with this access point, or at least the jitter looks okay on the upload path, for example. So it was just an illustration. We could imagine something else.
Sure. Okay, thank you. First question from Omar.
That's me.
Yep.
Yeah, I have a clarifying question to Francois. Is the intention to use a periodic sharing of the information, such as once 5 minutes, or is the intention to use real-time polling so that the most up-to-date jitter distribution will be accessible?
So could be anything, but what I was thinking is that maybe for Linux you can look at the Wi-Fi driver and look at the delivery time of each frame. So you remember when you sent the first time one frame and the last time and the time when it's finally acknowledged, and that's a way to measure the delivery time. So you can have a distribution of the delivery time of each frame, and so you can also have an idea of the jitter. So it could be shared among all applications.
Follow-up clarifying question. Is your intention to share information from access point or from the Wi-Fi driver on the device?
It's easier on the device directly, but we could imagine that the access point could send it in their beacon frames, for example, something like that. But I guess on the device it's easier, but you only have the upload path in that case.
Okay, thank you. Okay, so we'll move over to the discussion portion. We have about half an hour for that. So again, please write +Q in the WebEx chat. I see a few questions coming in now. So Vivi first.
Thank you. Thank you for all the presentations. I have a question to François. My question is, I mean, the idea is good, but my concern is if you start showing folks like this access point is better than that access point, then let's say this is a university campus, university network, then everybody will try to switch to the one that is best, and then that will get congested and so on, you know? So, I mean, giving user a choice to select, sure, but if it switches from one to another, then I don't know how it helps. And if it's automatic, maybe, you know, that is a better approach perhaps, but I'm a little concerned about how this is going to work. The second question or the concern that I had is, let's say we are talking about the home network where we don't have multiple access point, we usually have one access point. And I'm not an expert in Wi-Fi, but I don't see that I can have different channels advertised from my access point. I can only see, I can set up 2.5 gigahertz or 5 gigahertz AP. So perhaps you can, you know, provide some insight on that as well.
Yeah, sure. I don't know if I can, if I have the time right now or if I have to.
Go ahead.
Okay. So for the first question with like when it's the user that has to decide, I agree with you here in the illustration. The thing was like, the idea is that the latency can be a tiebreaker between different access points, but if an access point has a lower latency, maybe it's not the best overall because maybe it has a poor bit rate. So that's why either we choose for the user, either we find a way to make them understand that, for example, these access points are good for real-time purposes, but not for bulk download and stuff, to limit the bandwidth utilization. I don't know if it answers the question, but for the second question, yeah, sure. So here it's an experiment with two different channels that I activated. So they are not available at the same time. It's just to say that the bitrate information and the maybe also the loss, the frame loss information is maybe not sufficient to determine the latency that you will have. So yes, it can be used to choose between access points, but also if you have only one access point, you can also send this information to the application so that they can do some stuff. Even if there is only one access point, you can maybe configure your playback buffer, for example, to make it able to take all the jitter in the buffer. Or if you have multipath with your smartphone, if you have the 4G access, you can tend to use, for example, another channel if the jitter is too high.
Okay, all right, thank you. We should move on. Stuart, you're up next.
Thank you. I've heard several mentions of DSCP marking, and I have reservations about that.
prioritization is a zero-sum game. It implicitly assumes a scarcity of bandwidth, so that for one flow to gain, another flow has to suffer. And DHCP marking for lower latency assumes that all buffers will forever be bloated. So the only answer is to move my traffic to a different bloated queue that happens to be mostly empty right now. But when that queue fills up, the delay comes back. For now, I'm deliberately ignoring Wi-Fi channel access and aggregation, because the elephant in the room is buffer bloat. Why focus on a few milliseconds of Wi-Fi channel access time when there's hundreds of milliseconds of buffer bloat? There's also been talk about different traffic patterns, which makes the problem seem intractable. There are so many things to study, but my intuition is if we provided high throughput, low delay, and low loss for all traffic, suddenly everything would work better. We might find out that all traffic actually wants the same thing. They want high throughput, low delay, and low loss.
Okay, thank you, Stuart. Dave?
I'm ending up trying to respond to 3 different things, so I'll have to queue myself up. I'll respond to Stuart's comment there. In scheduling better at the access point, we have generally found that the access point using just the BEQ can do a much better job than trying to maintain 4 different queues of differing priority based on how the underlying MAC actually works. For clients, the issue is a bit more vague. So it definitely should be a subject of more research, but scheduling better and handling buffer bloat better for 1 queue is a lot easier than handling it for 4 separate hardware queues with different characteristics. If I still have 20 seconds left.
I'll give you 15.
15. We talked about the latency issues. Some of my work will really impact that metric. I liked very much the idea of a better icon. Presently today, we are typically measuring how good the connection to us is, but we're not measuring the connection from us to the access point. And there's a lot of good stuff in the latest Wi-Fi standards that will allow us to measure that bidirectional connectivity, and maybe we could be reflecting that in an icon that users could see.
Okay, thank you very much. Bob?
Hi. Yeah, I want to talk about Francois' talk as well. That was nice. I just wanted to make the point in your plot of throughput and latency and which applications use more of one or more of the other. I think that's not really an intrinsic property of the applications. It's just an intrinsic property of the way we currently do low latency. And I'm sure there would be applications that would want to be high bandwidth and low latency if you could do both. And so that's really a problem to solve. Not it's not an intrinsic thing that all games are low throughput because they want low latency. I'm sure someone would want to make a high throughput game if they could do both.
Yeah, I agree. It was a bad idea to do a Pareto curve for that.
No, it's not a bad idea. It's just it's an
I
interesting
agree.
comment on society at the moment, if you like.
Okay, thank you, Bob. Al?
Thanks, Sam. Thanks for all the good talks and sharing the data. The point I kept coming up against was the choice of access point and the frequency bands. For users who are knowledgeable, this has been kind of an arms race where you find that your 2 gig bands are full and 5 gig became available, so you had to buy some new equipment in order to jump in and take advantage of it. And specifically to Ken, in the US, when's the 6 gigahertz band going to become available to us? I'm in a multi-dwelling unit now, and the SSID situation is really clogged. Let's just put it that way. I've become much more aware of my Wi-Fi performance than anything else. Thanks.
I guess I'll take that. So thanks, Al. So I would suggest to solve your congestion problem there that you move.
Well, I just moved. I'm not going to move again.
Our operation is now open in the United States And there are Wi-Fi 6E equipments that can do it.
Okay. So I just need to go shopping and I'll fix this problem.
Well, that's low power. It's not the greatest. What you really want is full power, allowing for outdoor. And that's basically waiting for us to kind of finish up the specs for allowing systems. It's called AFC, Automatic Frequency Coordination. But for allowing systems that allow us to share the spectrum with incumbent microwave, point-to-point microwave links, which, because they're point-to-point links, they don't use up a lot of geographic space. So that's the trick there.
Okay, thank you.
It should be a year or two, or even less. It's coming out right now.
Thank you. Taurus?
So I would like to take up Stuart on the fact that the way I heard it, one policy for all packets fits all. I think that's especially not true on Wi-Fi, given the wide variety of nerd knobs to optimize transmission for different targets, even as much as 10 years ago in Wi-Fi, right? So just to name two of the most important ones is you can define different amount of spectrum time for different classes, and you can also define different amount of retransmissions, right? So for something like typical best effort traffic for the internet, you would have quite a few retransmissions, but that introduces quite a bit of latency, even if it's just a local Wi-Fi link. And then on the other hand, for something like real-time traffic, you would do fewer retransmission, but you reserve a much more of the spectrum bandwidth, right? So yeah, I think the differentiation of QoS for different classes of service is especially, I think, underutilized in Wi-Fi.
Okay, thank you, Taurus. Cohen?
Yeah, I also wanted to come back on the same topic related to DiffServ. I agree with Stuart, and also Dave mentioned that a lot of queues and maybe not queues, but different channel qualities, they pose a lot of problems related to managing latency, because your best efforts, let's say, what is it called in Wi-Fi, TID, if that is bursting out for a very long time, if then it's not low latency, then your other channel access channel types, they will also kind of have to wait for it at the end. So and mixing them with different rate priorities, that was one of the points I wanted to make. They get another rate priority, and if you cannot couple their fairness together, it's becoming very complex, and especially if you have Wi-Fi beacons of different users, separate access points, even in mesh networks, it becomes very complex. So it's better to have a lower layer which is very flexible and low latency, and build on top of that the different, even if you want DiffServ or the different alpha-REST, non-alpha-REST classes, instead of having a lower layer, which is also doing or trying to do a lot of smart things for improving either rates and latency at the same time, because it's not possible to do the two things at the same time. You have to do one, you have to make sure it can do both actually at the same time, all the time.
Okay, thank you very much. Jim, I don't know if you had a question for Stuart or if you were just agreeing with him. I assume you're agreeing. Okay, Vidi?
Hi again. Just for the folks who presented about Wi-Fi packet loss and retransmission, I saw one slide where it said there's a 70% probability of retransmission. I don't know who presented it, but I just want to ask just the general audience or anyone who knows, what's the main reason for transmission of Wi-Fi? Is it corruption, congestion? Is it interference? So if anybody has answers on that, please, yeah, let me know.
Okay, thank you. Dave?
To briefly answer that, yes is the answer to that. We see retransmissions at the lowest level MAC layer, sometimes up to 30 or more, based on corruption from various and sundry sources. It is one of the most unchecked aspects of the modern Wi-Fi standards that have not been adopted by any good algorithms to manage better. It was one of the things I intended to address in the Make Wi-Fi Fast project. As load got bigger, haven't got there. Actually, why I got to this question, though, is I wanted to ask for a point of information from Ken regarding the 6E standard. The FCC had mandated a centralized database at one point to coordinate spectrum selection for outdoor access points. I've lost track of that work, and I was curious as to what the current state is.
Yeah. So first of all, you're right about the retransmissions. There's all kinds of reasons. There's a number of, different thresholds to declare the medium empty and timings, and they don't always particularly work perfectly. So, you get collisions and things like that. You get interference, blah, blah, blah. Then you get retransmissions. To the FCC, first of all, this is just the United States, right? We're still working on gaining access to the full 6 gigahertz in Europe and other parts of the world. That's work that needs to progress. So the FCC has a process now where they'll somewhat bless different AFC system providers. And they all use the same ULS database that tells you where the microwaves are and where they're pointing and all that sort of thing. They access that, and then the system provider does a calculation based on certain parameters, and then that feeds down into the AP itself. Actually, before that happens, the AP has to register and say, I'm at this location and I'm at this height. The height thing's kind of an issue, but there's ways of doing that. And then, the system will say you're clear to use all these channels, or maybe some channels with some power limits. It's kind of decentralized at this point. It's not just purely under the control of one.
Okay, so as a point of question, where is that work actively taking place today?
In Wi-Fi Alliance, unsurprisingly, the AFC group, but they don't really have jurisdiction. That has to go, to the FCC. In Wi-Fi Alliance, we only provide guidance and guidelines and specs that they actually do use, but they don't have the force of the FCC until.
Okay, let's move on. Michael, thank you very much for that.
Okay, I'll blow the same horn as Torles regarding the DSCP matter. I think that given the thought model of one common bottleneck and all the packets hit it, and now we have a large queue and we need to differentiate between all those flows, I would rather have no queue and not differentiate. I am fully on that, but I also think that there are, having the DSCP marks could be used for various other interesting things. Now, I have heard Cohen's words of caution. I agree that probably it needs to be used very cautiously at the link layer if it's used there. But to give one example, this lower effort DSCP could really be used for various purposes that, you could put it on other paths, you could let it wait, you could buffer it for a while, you could let it get out of the way. All kinds of interesting and probably good things could be done if that marking was available. So I tend to think that we should probably offer the marks. As a way to give the network a bit more freedom to do interesting things with it. But not within that model of, having a large queue and scheduling. Okay, I should stop.
Okay, thank you very much. I think you've got a follow-up coming up soon. Evgeny? Evgeny, are you there?
Sorry, I was, now I can speak. Thank you. So I have 2 comments. The first one is related to the queuing in Wi-Fi, actually, and packet processing in Wi-Fi. Actually, in Wi-Fi, we have a lot of, in the standard of Wi-Fi, we have a lot of solutions which unfortunately are not widely implemented. For example, we can significantly improve channel access. We can improve quality of service. We have scheduling access, but unfortunately, almost all vendors do not support all this functionality. So this is an issue because we have really very rich standard, but many of solutions are not used. Why? It's a question, we can discuss it. And the second comment is related to, again, to queuing in Wi-Fi, but to buffering in Wi-Fi. Actually, the situation is as follows. So today, Wi-Fi has very high data rates, nominal data rates, and to improve efficiency and to reduce overhead, which is related to channel access, to preambles, to all this stuff, to acknowledgements, we need to transmit a lot of packets in a batch. It's called aggregation. And the latest version of Wi-Fi allows to aggregate 1,000 of packets together, which means that it's like 1 megabyte. So talking about buffer blocks and all this issue, from the efficiency point of view, sometimes it's worth to have many packets in the buffer to reduce, to improve spectrum utilization. So this is a trade-off maybe between several issues, and what is the optimal solution is a question. Thank you.
Thank you very much. Okay, Ken, did you have anything else you wanted to add? You're still in the queue.
Was that Cone or Ken?
Ken.
I'll always throw in my 2 cents. But on that last one, I'm a little bit surprised to hear people saying they don't like, the access categories and Wi-Fi. I'd like to understand that more, see what we could do about it. My opinion had been, we've got these 4 access categories and they're sort of not really used much. And some equipment can do that itself. And other than that, it's not particularly standardized. We do have a new spec in the Wi-Fi Alliance that we're quite happy about for QoS management, and in particular, there's a version called mirrored stream classification, and that's where I'm sorry, the client devices, the stations themselves can decide, well, this application really needs high bandwidth, this one needs low latency, and send that information up to the AP, which then does the stream classification back down again. And the clients, when you think about an application, the application kind of knows what it needs, not so much the network. And so that's the thought, is the applications now have a way of providing these priority levels, hopefully, more scheduling in the future.
Okay, thank you. Torlas?
Yeah, so the answer is, of course, always microwaves. No, actually, as much as 8 years ago, commercial or professional access points started to be able, with even, deep neural learning, be able to differentiate up to 50 different type of sources of problems with spectrum analysis and behavior of the traffic, right? So, I mean, there is a lot of very interesting commercial stuff out there. But to give the very simple example, right, you may simply have from something flying through, or, microwave or something, 1 second of outage, no traffic at all. So now think about how you would deal with 2 different applications, right? A Netflix flow wouldn't bother at all about this, right? This is not the congestion point. This is just one point that had 1 second outage, and you basically are going to retransmit within the access point to the client that burst of 1 second data 1 second later. No congestion incurred, but you have incurred 1 second of latency. You really wouldn't want the end-to-end congestion control to pick up on that. Then on the other hand, you have a live video conference. Well, I mean, you don't want to have latency. You would rather see all the 1 second just a black picture. You can't do all of that with just one traffic class through the access point.
Okay, thank you very much. Stuart?
Thank you. Quick reply to Ken on Wi-Fi traffic classes. Tolas talked about node knobs for Wi-Fi and different spectrum reservations for different traffic classes. That requires arbitrary value judgments about what traffic deserves to go in what class. And it presupposes we can't give good service to all traffic. So we have to give good service only to a privileged minority. I also disagree with the very commonly expressed view that video conferencing traffic would prefer packets to be lost instead of delayed. That might have been true before we had video compression, but these days traffic is highly compressed. Frames are sent as deltas from the last frame, and you can't decode the current frame if you've lost the previous frame it depends on. So even if a packet arrives too late to display, that doesn't make it useless. You still need it to construct the next frame. One video conferencing system I know about had a packet expiry time at the driver level, and if a packet couldn't be sent in time before the deadline, it was discarded before it even left the device. The result of this is a complete stream set requiring to begin again with a brand new keyframe. So the intentional discard of a single packet because it would have arrived late resulted in the transmissions of hundreds more packets to recover from that single loss. So video conferencing is not that different to file transfer in today's world with heavy compression.
Okay, thank you very much. We've got quite a queue to get through. Jim?
I'd like to raise a flag that whether it's Wi-Fi or cellular systems are very complex beasts. If you want to understand all the different, or a bunch of the different things that have been broken in Wi-Fi, then you should go read Toki's thesis. And some of those are common in other radio technologies. Some of those problems are not. So I give a very strong plug for to Toki's thesis. It is possible as to have, at least in Wi-Fi, something close to our cake and eat it too, as his thesis has shown. Basically, something approaching 2 orders of magnitude improvement of latency under load, which is why I said earlier I can walk around my house and teleconference at the same time as I'm doing bulk transfer. So what Stuart says is right on, and it is possible. There is an existence proof. And a few of the device drivers in Linux now know how to do this right. But it's not just the driver, it's a layer above.
Okay, thank you very much. We need to be very brief with questions now because we're going to run over time. Dave, I believe you're next. Dave? Okay, can't get any briefer than that. Omer?
Probably I'm going to start beating a dead horse here, but I was going to say that the assumption that a single flow on a network represents a single service class is getting less and less and less realistic. Consider, for example, a quick connection that contains a few streams which are used for metadata and should have lower priority but require high availability, while other streams require higher priority but can be dropped. Such stream represents an entire video conference that can be routed cohesively and thus avoid phase interference when different parts of the stream arrive at different time. However, what can we say about such stream? Is it real time? Yes. Is it best effort? Yes. Is it guaranteed delivery? Yes. Is it guaranteed delivery? No. I mean, it becomes more and more and more mute. So to that point, probably just making the transport be blazing fast and utterly stupid. Probably that's the approach.
All right, thank you. Dave, I think you have another question. Okay, I think we've lost Dave. Okay, Corey?
Go ahead, I'm done.
Okay, I was just going to stress that we're talking a lot here about performance, and performance is mainly governed by latency. So if you want buffer management, the diff-serve thing is orthogonal. If you know what you want from the network, it doesn't hurt to tell the network what to do, but there's no point in describing your traffic because it doesn't know what to do with the traffic description of video conference. if I put my other hat on, if I want to measure this, I need to know what the network's going to do with my traffic. So there's a little bit of information needed back from the network to interpret the performance of these apps that want to do clever things with the network. So there's a bit of a two-way couple here that we have to really get to grips with, and I haven't got time to talk about. So that was my suggestion.
Okay, thank you. Cohen?
Yeah, on the same topic, related to giving more information, definitely it will help. I think knowing whether you need retransmission or not, it could help. Whether it's always really necessary, there was already that discussion. But then it should be coupled to link layer classes and big categories and things like that. I think that's well, dangerous, and the coupling is not always there. So it should be done on a kind of higher layer where you give that information and use that on a more flexible and intelligent way, I would say.
Okay, thank you. Omer, did you still have another question? Or another thought?
No, skip. Roberto may have one.
I think we've still got some more in the queue. We've got Taurus next.
I would just like to reaffirm that I think what Stuart was saying about, loss is not a good thing for real-time traffic. But I don't think that answered to my example that I gave, right? So if you have 1 second of interruption where there is no traffic flowing, playing out, a live video conference packet 1 second too late is just going to give you, a round-trip experience of a latency of 1 second, right? So that doesn't help. And there are a lot of things that are done in codecs, in the higher-end professional video codecs that are doing things like, non-referenced frames, subsizing IDR frames with just incremental updates, layered codecs to reduce the quality, that are able to very well adopt while maintaining low latency to all type of impairments. And I think it would be highly educational to compare the experienced video quality for the user between those best-in-class commercial video conferencing systems to, I'll have to say, unfortunately, really, the worst possible video codecs, which is what you typically see in RTC web browsers, right? Because they're base class and they're not being sold for a lot of money. So make that comparison under all type of impairments.
Okay, thank you very much. Mikhail?
My comment is twofold. First, about the retransmissions. It's not only the interference for 1 second which can worsen the situation, but we just in wireless they just choose the coding, the redundancy, so that the probability of retransmission for a single packet is around 10%. So it's just the matter of efficient wireless channel usage. And the second part was about, are we able to give anyone good performance? Maybe yes, while we have similar delay requirements or similar order of delays. But if we have virtual reality and etc., those applications will require much less delays, and it's just will be difficult to meet them with video streaming.
Okay, thank you. We can just squeeze in Roberto for one last thought.
Thank you. As I posted in the Slack as well, I think that it would make sense to allow applications to state much more richly the behavior they would wish the network to apply to the packets. So the most controversial thing I'm likely to say is that I wish that all our clocks were synchronized. And so I could put a clock time in the packet beyond which you should no longer bother to retry. And then, of course, there should also be a separate thing, which is to max the total amount of, bound to the total amount of duplicate effort that the network should do on the application's behalf, which is effectively the same as a TTL like we have today, although not measured in hops, measured in retries. All of this, of course, is assuming that we would have a theoretical network where the links could do retries on behalf of the flow, not just the end-to-end thing. And if we consider things like the interplanetary network thing, which of course is a wonderful thought experiment and not really relevant to most of our customers, it's very clear that you don't want end-to-end retransmission when you can have link-to-link retransmission for many of these things. So there you go. I just wish that the applications could say better what their actual thoughts were or actual requirements were with regards to latency, so the network doesn't mess up, doesn't overcommit, and minimizes the total amount of wasted effort.
Okay, thank you. Over to you, Wes. I think we're done with this section.
Okay, Jenny might close us out if he's here. All right, well, I'll do it. Thank you all. It was a great discussion. It's fantastic when we keep bumping up against the end of the time. That means that it was an interesting discussion that people wanted to participate in. So good day 2. We'll start day 3 tomorrow. As a reminder, I'm going to stop the recording, and then I did create 6 breakout sessions, and you guys can sort of discuss when or what breakout sessions you want to join to continue discussions. I know there was at least talk of 1 or 2 that we're going to run. So we'll keep those open for at least an hour or until people run out of steam. Yesterday there was 4 active groups for at least an hour. So thanks everybody, and talk to you tomorrow.
Where to find these breakouts? I can't see them on
You should see a breakout session button at the bottom or somewhere. I guess somebody said it was near the participants window.
Click on the participants drop down in the WebEx application, and then you'll see a green thing that says show all breakout sessions.